Something changed about the planet you are standing on. Earth is spinning faster than it has in 50 years. Days are getting shorter. Atomic clocks are drifting out of sync with the ground beneath them. Satellites are measuring it. Scientists have confirmed it. And the causes run deeper than most people have any reason to suspect. Liquid iron surging miles below your feet. Ice sheets collapsing and physically reshuffling the planet's weight. Something happening at Earth's very center that researchers are still working to fully explain. We are going to cover all of it: the core, the clocks, the ice, the magnetic field, and what it means for the systems that every person on Earth depends on. We begin now. On June 29th, 2022, something quietly historic happened. Earth completed one full rotation in less time than it ever had since scientists began measuring with atomic precision. The day was shorter than normal by 1.59 milliseconds. That sounds like nothing. A blink. A fraction so small it feels irrelevant. It is not irrelevant. When a planet 4.5 billion years old suddenly starts rushing through its own rotation cycle, faster than at any recorded point in the modern era, scientists pay attention. And when it happens not once, but repeatedly, across multiple years in a row, the question shifts from whether it is real to what on Earth is driving it. The answer involves nearly every major system on the planet at once. To understand what faster spinning actually means, picture a clock, not a digital clock on your phone, but the planet itself, turning once every 24 hours. That 24-hour day is not a fixed number. It never was. Earth's rotation has always fluctuated slightly, slowing and speeding by tiny amounts, depending on forces acting on it from both the inside and the outside. For most of recorded history, the planet was gradually slowing down. Tidal friction from the moon pulls at the oceans like a brake, dragging on the rotation millisecond by millisecond across millions of years. Ancient coral fossils tell us that 400 million years ago, a year had more than 400 days. The days were shorter because the planet was spinning faster. Over time, it slowed. That long, steady deceleration is the baseline. It is the expected direction of travel, which is exactly why what began happening around 2016 stopped researchers cold. The trend reversed. Earth started speeding up. Not dramatically, not in a way you would feel during your morning coffee, but measurably, consistently. Year after year, the planet logged some of the shortest days ever recorded with modern instrumentation. 2020 set the record at the time. 2021 broke it. 2022 shattered it again. Here's what makes this genuinely strange, beyond the numbers alone. The forces that cause gradual slowing have not disappeared. The moon is still pulling on the oceans. Tidal friction is still operating exactly as expected. Something else is now pushing in the opposite direction hard enough, persistently enough, to overcome that ancient braking mechanism. That is the puzzle. And the candidates responsible for this reversal reach from the surface of the planet all the way down to its core. At the surface, melting ice is redistributing mass across the globe in ways that physically alter the spin. In the atmosphere, shifting pressure systems push against the rotating crust. In the oceans, changing current patterns apply their own subtle drag and release. And deep underground, a churning ocean of liquid iron more than 2,000 miles below your feet moves in ways that couple directly to the rotation of everything above it. Each of these forces is confirmed. Each is measurable. What scientists are still working out is precisely how they interact, which one is dominant at any given moment, and whether the acceleration we are currently observing is building towards something or approaching a reversal of its own. What we know for certain is this: the planet is not behaving the way the models expected. The systems built to track time, synchronize satellites, and coordinate global infrastructure were designed around a slower Earth. They are now running behind, and the gap between atomic time and Earth time is forcing a decision that engineers have openly described as potentially catastrophic for the internet. That story starts with a single invention, designed to fix a problem that almost nobody saw coming. A millisecond feels meaningless. You cannot feel it. You cannot see it. If someone removed 1 millisecond from your day, you would never know. But Earth is not a person. Earth is a system of systems, all synchronized to one another by the rhythm of rotation. And when that rhythm changes, even by a fraction of a millisecond per day, the ripple moves through every layer of that interconnected system. Here is the clearest way to picture it. Imagine a massive spinning wheel. Every component attached to that wheel, every gear, every linked mechanism, is calibrated to turn at the same rate. Now speed that wheel up slightly. Nothing breaks immediately, but every connected part begins to drift out of phase with the timing it was built around. The longer the mismatch runs, the further the drift. And the further the drift, the more pressure builds on the connections holding everything together. Earth's rotation is that wheel. The connected systems are everything human civilization has built to depend on precise time. Consider the global positioning system first. Satellites orbit at a specific altitude and broadcast signals timed to nanosecond precision. They are synchronized to atomic time, which is anchored to the behavior of cesium atoms, not to the spin of the planet below. When Earth turns slightly faster, the planet's surface moves ahead of where the satellites expect it to be. The position data shifts, not by miles, not even by feet, by centimeters. But in aviation navigation, in surgical robotics, and in autonomous vehicle guidance systems, centimeters matter in ways that ordinary passengers never have reason to consider. Financial systems represent another layer of this problem. Stock exchanges in New York, London, Tokyo, and Frankfurt execute millions of trades per second. Each transaction carries a timestamp accurate to the microsecond. Those timestamps are synchronized to coordinated universal time, which is itself anchored to atomic clocks. A desynchronized planet creates a desynchronized timestamp, and in high-frequency trading, even a microsecond of ambiguity can represent millions of dollars of exposure and enormous legal liability. Power grids are perhaps the most viscerally physical example of all. Alternating current flows at a fixed frequency, either 50 or 60 cycles per second, depending on the country. Grid operators synchronize their systems to universal time to balance load across regions that may span thousands of miles. When time drifts, load balancing drifts with it. The consequences may begin invisibly, but they do not remain invisible. Now here's the layer most people never think about. All of this was already accounted for. Scientists knew Earth's rotation was imperfect. That is why the leap second was invented in 1972. Periodically, 1 extra second would be added to the official clock to keep atomic time aligned with Earth time. It was a patch, a small correction applied whenever the gap between the two grew too large to ignore. 27 leap seconds have been added since the system began. Not one has ever been removed. The planet was always slowing, which meant atomic clocks always ran ahead of the planet, which meant the fix was always to add time. Now the planet is speeding up. Atomic clocks are falling behind, and for the first time in the history of the entire timekeeping system, the discussion has shifted to removing a second from the official clock rather than adding one. That is called a negative leap second. And the engineers responsible for internet infrastructure have described it, on the record, as one of the most dangerous single events that could happen to global digital systems. 1 second backward. The consequences of that single subtraction are stranger and more serious than almost anyone outside the field realizes. But before we get there, we need to understand the instrument that detected this acceleration in the first place. Because what atomic clocks actually are, and how they managed to catch a planet speeding up, is a story that begins inside a single, impossibly small, vibrating atom. Before 1955, the most accurate clocks on Earth lost or gained about 1 second every 300 years. That sounds impressively precise. By the standards of daily life, it was extraordinary. By the standards of planetary science, it was nowhere near good enough to measure something as subtle as a gradual shift in how fast the world was turning. Then physicists built the first atomic clock. The principle is elegant in its simplicity. Atoms do not lie. Every atom of the same element anywhere in the universe vibrates at exactly the same frequency. Cesium, 133 atoms, the type used in the most precise atomic clocks, oscillate 9,192,631,770 times per second. Every single time, without exception, without drift, without variation. That frequency became the new definition of a second. not a fraction of Earth's orbit around the Sun, not a pendulum swing calibrated in a particular workshop. The vibration of a single type of atom counted 9 billion times over. The result was a clock so accurate it would not gain or lose a single second across 300 million years. With that level of precision suddenly available, scientists could do something they had never been able to do before. They could measure the planet in real time with genuine fidelity. And what they found was unsettling from the beginning. Earth's rotation, it turned out, was messy. It fluctuated constantly. The planet sped up slightly in winter in the northern hemisphere, as atmospheric mass shifted toward the poles. It slowed again in summer. Large earthquakes made tiny adjustments. Major storms applied measurable pressure to the crust. El Niño events, shifts in deep ocean circulation, even large accumulations of snow at high latitudes. All of these left faint signatures in the rotation data, the way a fingerprint leaves a trace on glass. Researchers cataloged these variations. They built models to account for them. The system worked. The leap second kept atomic time and Earth time from drifting too far apart. Everything was manageable, if never perfectly clean. Then came the data from 2016 onward. The fluctuations were still there, exactly as before. But underneath them, a clear signal was emerging. The average length of a day was shrinking. Not randomly, not as a seasonal variation that would reverse itself the following year. As a trend year after year, the averages were falling in one direction, with the kind of quiet persistence that catches the eye of anyone who knows how to read these records. The first response in the scientific community was exactly what you would expect from careful professionals. Check the instruments. Rule out calibration errors. Cross-reference data from atomic clock networks in different countries, on different continents, maintained by different teams operating under different funding structures. The International Earth Rotation and Reference Systems Service, the organization that monitors this globally from its headquarters in Paris, ran the checks. The instruments were functioning correctly. The signal was real. Here is the detail that stopped researchers mid-sentence when they encountered it in the data. The acceleration was not explained by any single known mechanism. Tidal friction was still operating as expected. Seasonal atmospheric shifts were accounted for. When scientists methodically subtracted every known contributing factor from the measured rotation data, a residual acceleration remained. Something beyond the cataloged causes was pushing the planet forward. They had a measurement without a complete explanation. In science, that situation is where things get genuinely interesting and occasionally alarming. Because the deeper researchers dug into what might explain the leftover signal, the more they found themselves looking not at the surface of the planet, not at the ice or the atmosphere, or the oceans, but straight down, 2,000 miles down, into a place no instrument has ever physically reached. A place where iron flows like a slow, vast ocean in total darkness under pressure that would crush any known material to powder in an instant. What they found moving down there may be the largest hidden driver of everything happening above it. In 1972, the world quietly agreed on a fix to a problem most people did not know existed. Atomic clocks were now the gold standard for time. They were anchored to physics, not to the planet. And the planet, as precise measurement had revealed, was an unreliable timekeeper. Its rotation fluctuated. It was gradually slowing down under tidal drag from the moon. And if nothing was done, atomic time and Earth time would drift further and further apart with every passing decade. That mattered for a specific and practical reason. Nearly all human systems navigation, communication, civil administration were built around the assumption that noon on a clock corresponded to the point when the sun sat highest in the sky. If clocks kept perfect atomic time while the planet slowed, eventually noon on the clock would arrive while the sky still showed late morning. Not next year, not next century for practical purposes, but across centuries, the drift would become undeniable and disruptive. The solution was the leap second. Once or twice a year, when the gap between atomic time and Earth time grew large enough to require correction, international timekeeping authorities would add a single extra second to the official clock. Clocks around the world would tick from 23 hours, 59 minutes, and 59 seconds to 23 hours, 59 minutes, and 60 seconds before rolling over to midnight. One extra heartbeat inserted into global time. It sounds clean and elegant. In practice, it was always awkward and occasionally disastrous. Computer systems are not designed for a minute that contains 61 seconds. Operating systems, databases, and network servers all handle that extra second in their own way, and they do not always agree. In 2012, a leap second simultaneously crashed servers at Reddit, LinkedIn, Qantas Airlines, and hundreds of other organizations. Engineers spent hours diagnosing what turned out to be a single added second interacting poorly with certain software scheduling systems. And that was a positive leap second time moving forward, adding something. Nobody had ever had to remove one. Here is the precise technical reality of a negative leap second. Clocks would tick from 23 hours, 59 minutes, and 58 seconds directly to midnight. 23 hours, 59 minutes, and 59 seconds would simply not exist. Every system expecting that second, every log file, every transaction, every scheduled process timed to that specific moment would encounter a gap, a hole in time, a moment that the clock insisted had already happened before it arrived. Engineers at Meta, the company that operates Facebook and Instagram and manages one of the largest server infrastructure networks in the world, published a detailed technical paper describing the potential consequences. They called a negative leap second an event with a devastating effect on software relying on timers or schedulers. Their recommendation was not to apply one at any point, ever. Instead, they argued for smearing the correction across a longer period, spreading the 1 second adjustment over many hours, rather than applying it as a single abrupt jump. The problem is that smearing creates its own category of inconsistencies. Different companies implement smearing differently. During the transition window, two systems comparing timestamps would be operating in subtly different versions of time, technically agreeing on what time it was in the abstract, but producing timestamps that disagreed by small but legally significant amounts. In 2022, an international standards body voted to eliminate the leap second entirely by 2035, allowing atomic time and Earth time to drift without correction, until the gap is handled through some different mechanism not yet fully specified. That decision may sound like a clean resolution to a difficult technical problem. It is not. It simply defers the problem, allowing a gap to grow instead of patching it in real time. And the gap is currently growing in a direction nobody designed the infrastructure to handle. Because as Earth keeps accelerating, that gap compounds, and the systems most vulnerable to it are not aging legacy platforms. They are the satellites positioning every aircraft, every ship, and every self-driving vehicle operating on Earth at this moment. Picture every major digital system on Earth as a choir. Each singer is a different server, satellite, database, or network node. They are all performing from the same sheet of music, coordinated universal time. Their job is to stay perfectly synchronized, matching each other note for note, millisecond for millisecond. Now remove one note from the score, without warning every singer at exactly the same moment. Some singers skip the note cleanly and move forward. Others pause, waiting for a note that never arrives. Others finish the bar early and leap ahead. In an instant, voices that were perfectly synchronized begin to split. The choir fractures. That is, in rough terms, what engineers fear from a negative leap second at scale. The internet runs on a protocol called the Network Time Protocol, which constantly synchronizes clocks across billions of devices worldwide. It was designed with the assumption that time moves forward. It was never engineered to handle time moving backward. When a system's internal clock suddenly reads 1 second earlier than it did a moment before, processes scheduled to run at a specific timestamp can trigger twice. Logs that record events in chronological order can record new events as if they occurred before old ones. Security certificates that verify identity using timestamp matching can fail entirely. Database entries can be duplicated, overwritten, or silently discarded. In financial markets, the damage is easier to quantify and harder to recover from. High-frequency trading systems execute thousands of transactions per second. Order books match buyers to sellers based on the precise sequence of submitted orders. If one exchange's clock steps backward, while another's does not, the sequence of trades becomes ambiguous. Transactions that appeared settled become disputed. Orders placed after the subtracted second might be logged as occurring before orders placed before it. Regulatory bodies in multiple jurisdictions require financial institutions to maintain records accurate to the microsecond. A 1-second reversal does not merely create confusion. It creates legal liability on a scale that settlements cannot easily address. Power grid operators face their own version of the same fundamental problem. Grid synchronization relies on timestamps to balance electricity loads between regions that may be hundreds of miles apart and operating under different demand conditions. A sudden discontinuity in time creates a window in which the coordination signal breaks down. In most cases, backup systems compensate within seconds. But the industry has a specific term for what happens in that gap: a synchronization event. And synchronization events, even brief ones, are recognized precursors to the kind of cascading failures that can take down large sections of a grid and leave cities dark for hours. Aviation adds yet another layer of consequence. Air traffic control systems depend on synchronized timestamps to track aircraft positions and to resolve potential conflicts between flight paths that may be separated by only a few miles of airspace at cruising altitude. When controllers at different facilities are working from clocks that disagree even briefly, even by fractions of a second, the margin built into separation standards gets consumed by the ambiguity. Aircraft that should be safely separated become uncertain in their relative positions. The math that controllers rely on to guarantee safety stops producing reliable answers. The world's largest technology organizations, Meta, Google, Amazon, Microsoft, have each developed their own internal approaches to dealing with potential timekeeping discontinuities. None of them arrived at exactly the same solution, which means that in the event of a negative leap second, the most powerful technology companies on Earth would be running on slightly different versions of what time it is simultaneously, without any coordinating mechanism to reconcile the differences. The international standards bodies chose to eliminate the leap second, rather than face that scenario. But the underlying problem, a planet rotating faster than the timekeeping infrastructure was designed to accommodate, does not disappear with a policy decision. It keeps compounding. And the force driving that acceleration is not coming from the surface. It is not primarily the ice or the atmosphere. The deepest signal in the data points, somewhere far more difficult to observe. Somewhere no human has ever been, and where no instrument has ever survived long enough to report back. Every time you use navigation on your phone, a quiet negotiation happens between your device and a constellation of satellites orbiting more than 12,000 miles above the surface. Those satellites do one essential thing. They broadcast a timestamp. Your device receives signals from at least 4 of them, compares the tiny differences in when each signal arrives, and uses those differences to calculate precisely where on Earth you are standing. The whole system depends on one foundational assumption: that the satellites know where Earth is not approximately, not to within a few feet, but to within centimeters at any given microsecond. Each GPS satellite carries multiple atomic clocks and orbits on a precisely calculated trajectory. Ground stations track those orbits continuously and send correction data to keep the satellite's position model accurate. The satellites, in turn, maintain a precise model of where Earth's surface should be at any given moment, based on the planet's expected rotation rate. When Earth rotates faster than the model predicts, the surface moves ahead of where the satellites think it should be. The error is small. Depending on the degree of mismatch, it might translate to a positional error of a few centimeters to a few meters. For a family navigating to a restaurant, that is irrelevant. For a cargo ship threading a narrow strait at night in poor visibility, it is the difference between a clean passage and a grounding. For a precision-guided landing system, or a surveying instrument building a tunnel from both ends simultaneously, it is simply not acceptable. Ground control teams correct for Earth's rotation variations continuously. It is not a new problem, and the systems have margins built in for it. But corrections are applied in updates, not in real time. Between updates, the system runs on its last known model of Earth's behavior. When the planet accelerates in ways the model did not anticipate, those updates lag behind reality. There is a gap brief, but real, during which the system is navigating on outdated information. There is a deeper issue that rarely appears in consumer technology reporting. The GPS network was not built alone. Russia operates GLONASS. The European Union operates Galileo. China operates Beidou. Each of these systems runs its own set of atomic clocks, its own ground correction stations, and its own mathematical model of Earth's orientation. They are all supposed to be coordinated to the same underlying time standard. But they do not update simultaneously, and their correction models do not always agree in their details. When Earth behaves predictably, the disagreements between the systems are negligible. Position fixes from different satellite constellations produce results that are essentially identical for practical purposes. When Earth accelerates in ways that push against the correction models, those disagreements widen. Devices that blend signals from multiple constellations to improve accuracy, which includes most modern aviation receivers and high-precision survey instruments, can begin receiving contradictory position data from different constellations at the same time. Aviation relies on blended satellite positioning more than almost any other field. Modern instrument approaches at airports use satellite guidance to bring aircraft to within feet of a runway in zero visibility in conditions where pilots cannot see the ground until they are barely above it. The tolerances are extraordinarily tight. The safety margins are real but not unlimited. They were calculated for a planet behaving within a defined range. When the planet moves outside that range, the margins shrink. This is why aviation authorities around the world issue what are called notices to airmen whenever unusual behavior is detected in timing or navigation systems. Those notices have been issued multiple times in recent years, specifically related to timing anomalies and satellite navigation irregularities. The sky is not falling. The engineers maintaining these systems are skilled and vigilant, but they are working harder than they were a decade ago to keep a planet-scale timing mismatch from propagating into systems that lives depend on. And the harder question, the one that keeps geophysicists up at night, is not what the mismatch costs us in terms of navigational precision. It is why the planet accelerated in the first place. The atmosphere contributes, the oceans contribute, the ice contributes. But underneath all of it, beneath every layer of explanation that sits within reach of human instruments, there is a force so deep and so strange that understanding it requires picturing something almost impossible to hold in the mind clearly. An ocean of liquid iron, 2,000 miles beneath your feet, moving in total darkness. The mechanism connecting core rotation to surface rotation runs through a principle so fundamental it appears in every introductory physics course. Yet its application at planetary scale produces effects that remain only partially understood even by the scientists who study them most closely. That principle is the conservation of angular momentum. When the inner core decelerates, when that ball of solid iron at the center of the planet slows its rotation, relative to the layers above it, the angular momentum it gives up does not vanish. It cannot vanish. It transfers. It moves outward through the liquid iron of the outer core, then through the pressure and electromagnetic coupling at the core-mantle boundary, then through the solid rock of the mantle itself, and eventually into the crust. Angular momentum moving upward through those layers is angular momentum being added to the rotation of the surface. The physical analogy most often used for this is the figure skater. A skater spinning with arms extended slows when they pull their arms inward. That is the classic demonstration of angular momentum conservation. Now run it backward. Imagine the skater releasing energy from the inside outward. As that energy travels from the innermost layer to the outermost, the outer part speeds up. The surface of Earth is that outer part. The inner core, releasing angular momentum upward through the layers, is the mechanical equivalent of the skater's arms pushing outward, and the planet's surface responds by spinning faster. The timeline is striking when you lay it out carefully. The inner core's apparent deceleration in the late 2000s and early 2010s, identified through the seismic data, aligns with an appropriate lag for transfer time through the layers, with a surface acceleration that became clearly measurable starting around 2016. That lag is itself scientifically significant. It tells researchers something important. The coupling between the innermost layer and the surface is not instantaneous. Information from the center of this planet takes years, possibly decades, to propagate fully upward through the layers. The Earth's interior communicates with its surface in geological slow motion, which raises a question that no one has a clean answer to yet. If the inner core reversal is real and continuing, what does the surface look like at the far end of this angular momentum transfer? Is the current acceleration a transient pulse that will fade as the transfer completes? Or is it the beginning of a prolonged shift in the planet's rotational regime, one that will interact with every other forcing system described in this account in ways that compound over decades. The answer, according to some researchers, may be written in the ice, because while the core drives things from the inside, something is happening at the poles that is reshaping the planet from the outside simultaneously, and the two forces are pulling at the same system from opposite directions. In physics classrooms, there is a demonstration that never fails to stop a room cold the first time students see it. A person sits on a freely rotating stool, holding two substantial weights, one in each hand, arms stretched wide. The stool spins slowly. Then they pull their arms inward, drawing the weights close to their body. The stool accelerates dramatically, without anyone applying a push, without any external energy being added to the system. The person simply moved mass closer to the axis of rotation. In doing so, they conserved angular momentum, and the rotation rate had to increase to compensate for the changed geometry. Earth operates on exactly this same principle, the same mathematics, the same physics, scaled up to planetary dimensions. For most of the last 20,000 years, massive ice sheets covered large portions of the planet's surface, concentrated primarily near the poles. Ice, sitting near the poles, sits close to Earth's rotation axis. When that ice melts and the water flows into the global ocean, the mass moves away from the poles and spreads across lower latitudes, moving away from the rotation axis. By the same physics as the stool demonstration, but run in reverse, pulling mass away from the axis should slow the rotation over the long term. For most of the Holocene, that post-glacial rebound effect has been doing exactly that, contributing to the long, gradual deceleration of Earth's spin that scientists had documented and come to expect. But something has changed in the rate of ice loss. The Greenland ice sheet and the West Antarctic ice sheet are now losing mass at rates that have accelerated sharply since the early 1990s and have continued steepening since. Greenland alone is losing roughly 280 billion metric tons of ice per year. Antarctica is losing roughly 150 billion metric tons per year. Those numbers are large enough to detect from space, not metaphorically, but literally, through changes in the planet's gravitational field measured by orbiting satellites. The mission responsible for this measurement is called GRACE, the Gravity Recovery and Climate Experiment, and its successor mission, GRACEFO. The concept behind it is precise and almost audacious in its simplicity. Two satellites flying close formation at a fixed altitude. They measure the distance between themselves continuously to within a fraction of a micrometer. When one satellite passes over a region with greater than average mass below it, a dense mountain range, a thick section of ice, an unusually deep concentration of ocean water, that satellite is pulled slightly ahead by the stronger gravitational attraction. The distance between the two satellites changes. By analyzing those changes continuously across every point on Earth's surface, scientists can produce detailed maps of where mass is increasing and where it is decreasing, updated regularly across years and decades. Using GRACE data, scientists have directly mapped the redistribution of mass as ice melts in real time. The picture is dramatic and unambiguous. The poles are losing mass. The mid-latitude ocean basins are gaining it. Earth's moment of inertia, the rotational equivalent of how mass is distributed relative to the spin axis, is shifting in real time and in a direction that the physics says should slow the rotation. In the long run, it will. The ongoing rebound of land, freed from ancient glacial weight, will continue to redistribute mass toward the poles for thousands of years, gradually acting as a brake on the rotation. But here's the short-term complication that matters for the present moment. The redistribution is not uniform. Different parts of the ice sheets melt at different rates in different seasons. Different ocean basins accumulate water at different depths and latitudes. The interaction between where mass is going and how that interacts with Earth's three-dimensional, irregularly shaped interior produces effects that are not simply the sum of their parts. One of those effects is that the planet's rotation axis is physically moving. Not the magnetic pole, the actual geographic spin axis. The imaginary line through the center of the planet around which all rotation occurs. It has shifted by measurable amounts over the past 20 years in a direction that aligns directly with the observed pattern of ice loss. This is confirmed by satellite data. It is not a model prediction. It is a measurement, And the implications of a shifting rotation axis reach into everything from the detailed mathematics of sea level rise projections to the long-term behavior of the magnetic field. For most of the 20th century, the geographic North Pole drifted slowly in one direction toward northern Canada at a rate of a few centimeters per year. The cause was primarily post-glacial rebound, the continuing, slow adjustment of Earth's crust and mantle to the removal of the massive ice sheets that covered North America and northern Europe during the last glacial maximum, which ended roughly 12,000 years ago. That ice was gone, but the land beneath it was still rising, still redistributing mass, still influencing the planet's rotational geometry with a lag measured in millennia. Then, around the year 2000, the direction of polar drift changed. It turned eastward toward Greenland. The rate increased substantially, from a few centimeters per year to roughly 17 centimeters per year over the course of the following 2 decades. When researchers analyzed the cause of that directional shift, the GRACE satellite data provided a clear answer. The primary driver was ice loss from Greenland. Greenland sits in a specific geographic position relative to the polar drift trajectory, and as its ice sheet loses mass at an accelerating rate, it changes the distribution of planetary mass in a way that pulls the rotation axis in a new direction. The correspondence between the onset of accelerated Greenland ice loss and the shift in polar drift direction is close enough that scientists treat them as directly and causally linked. Ice loss from West Antarctica has also contributed to the shift, pulling the axis in a slightly different direction and adding to the net eastward trend. The result is that the actual geographic pole, the point on the surface directly above Earth's rotation axis, is now located somewhere measurably different from where it was when most of the people reading these words were born. This is not a dramatic shift in the planet's orientation that would change the seasons or move the constellations in the night sky, not on any human timescale, but at the precision required by satellite systems, geodetic surveys, and time transfer infrastructure, it matters considerably. Every system that uses the precise location of Earth's rotation axis in its calculations must be updated to account for the drift. The International Earth Rotation and Reference Systems Service publishes updated Earth orientation parameters regularly, and those parameters feed directly into the correction models used by every satellite navigation system operating globally. The updates have been coming faster and requiring larger corrections in recent years, and the rate of ice loss is not slowing, it is accelerating. Models from the early 2000s consistently underestimated how quickly the ice sheets would respond to atmospheric and ocean warming. The actual observational data has outpaced multiple generations of projections. If the ice loss rate continues to increase, the polar drift will also continue to accelerate. The axis will move faster. Corrections will need to be applied more frequently. And there is a second-order effect that compounds the problem. The mass redistribution from ice loss changes the planet's moment of inertia in a way that alters how Earth responds to other forces acting on it. It does not just shift the axis. It changes the planet's rotational response to perturbations that have existed for billions of years. One of those perturbations is a slow, rhythmic rocking that geophysicists have tracked for over a century. It has been one of the most reliable and predictable features of Earth's rotational behavior for as long as instruments could measure it. In the early 2000s, it nearly stopped. Earth does not spin on a perfectly stable axis. It wobbles. It has always wobbled. Multiple overlapping wobbles, each with its own period and its own physical cause, combine into a complex and shifting drift of the geographic poles that scientists have been tracking with increasing precision since the late 19th century. The one that concerns us here is called the Chandler Wobble, named after the American astronomer Seth Carlo Chandler, who documented it in the 1890s after noticing that the position of the pole traced a small, looping path that repeated roughly every 14 months. The cause is geometry. Earth is not a perfect sphere. It is slightly flattened at the poles and bulging at the equator, an oblate spheroid, shaped the way a ball of soft clay looks when you press it gently between your palms. A non-spherical rotating object does not spin in perfect alignment with its geometric axis. It wobbles around it, the way a football tumbles slightly as it spirals through the air, or the way a spinning top traces a slight cone rather than a perfectly vertical line. For a rigid body, this wobble should damp out over time as friction dissipates the energy. But Earth is not perfectly rigid. The crust flexes under tidal loading, the mantle flows, extremely slowly but measurably. The oceans slosh. These flexibilities continuously re-excite the wobble, feeding it energy that compensates for the dissipation and keeps it going. The Chandler wobble traces a small circle roughly 30 feet across at the pole, an almost impossibly small displacement when set against the planet's size, yet measurable with precision instruments. Superimposed on it is an annual wobble caused by seasonal shifts in atmospheric mass and ocean loading. The combination of the two produces a beat frequency that traces a slightly irregular ellipse over periods of about 6 years. It has been one of the most predictable features of Earth's rotational behavior for as long as the records go back. Then around the year 2000, it started behaving differently. The amplitude of the wobble, the size of the circle traced by the pole, began to decrease. By around 2005 to 2006, the Chandler wobble had dropped to roughly 1/5 of its typical amplitude. It had nearly vanished. Not completely, but dramatically, in a way that had no obvious precedent in the available record. This was noticed. Papers were written. The scientific community engaged in the kind of focused, careful debate that important anomalies deserve. The leading hypothesis pointed to a redistribution of pressure at the deep ocean floor. Cold, dense water. The water that sinks to the bottom of the ocean in specific regions, like the North Atlantic and the Southern Ocean. In a process driven by temperature and salinity differences, had shifted in its geographic distribution in a way that altered the pressure pattern on the ocean floor. That altered pressure pattern changed how efficiently the Chandler wobble was being re-excited by the ocean. Ocean temperature changes associated with a prolonged La Niña cycle were identified as a probable contributing factor. The wobble eventually recovered. By the late 2010s, it was operating closer to its normal amplitude again. The system demonstrated a degree of resilience, but the episode left something uncomfortable in the minds of the researchers who studied it most carefully. A feature as fundamental as the Chandler wobble operating continuously for as long as Earth has had its current shape, driven by the planet's own geometry, had been significantly suppressed by changes in ocean circulation patterns. Changes that were themselves driven by surface temperature anomalies tied to a climate cycle. If ocean circulation changes could do that to the Chandler wobble, other changes could suppress or amplify other fundamental rotational features. And the ice redistribution, the ocean warming, and the core dynamics currently underway represent changes considerably larger and more persistent than a single La Niña event. The combination of effects on Earth rotation, if all the currently observed trends continue and compound, could take the system outside any behavior observed in the modern instrumental record. At that point, the only reliable reference would be the deep past, the geological archive written in ancient rocks, coral skeletons, and seafloor sediments, recording how Earth behaved during the last time conditions were remotely comparable. And that archive contains information that challenges some comfortable assumptions. But before we reach back into geological time, there is another layer in the present-day picture that has not yet been addressed. A region of the planet where the magnetic field has already weakened by more than 20% compared to its typical strength. A region that sits directly over one of the most densely populated areas of the southern hemisphere. A region that, based on the data currently available, may be in the process of splitting into two. Earth's magnetic field is not uniform. It does not wrap the planet in a symmetrical, evenly distributed shell. It is generated by the turbulent, asymmetric flow of liquid iron in the outer core, and the result is a field with significant regional variation, stronger in some areas, weaker in others, shifting in both strength and geographic extent over decades and centuries as the core flows that generate it evolve. Most of those regional variations are minor enough that they do not attract sustained scientific attention. But one region stands out, and has been standing out with increasing prominence for the better part of a century. The South Atlantic Anomaly is a large region centered roughly over the South Atlantic Ocean, and extending across much of South America where the magnetic field is significantly weaker than the global average. In the strongest portion of the anomaly, the area of greatest weakness, the field is roughly 40% weaker than it would be at equivalent latitudes in other parts of the world. That weakness is not merely an abstract measurement. It has direct observable consequences for objects operating at altitude. Earth's magnetic field deflects charged particles, arriving from the sun, protons, and electrons, moving at hundreds of miles per second, in what is called the solar wind, as well as higher energy cosmic rays arriving from beyond the solar system. In most parts of the world, this protection begins at a sufficient altitude that satellites in low Earth orbit are comfortably shielded from the radiation environment they would otherwise encounter. In the South Atlantic anomaly, the field is so weak at lower altitudes that charged particles penetrate further before being deflected. Satellites passing through this region encounter elevated radiation levels that can cause electronic malfunctions, bit flips in memory, processor errors, and sensor noise that can corrupt data or trigger unintended commands. The International Space Station routinely takes extra precautions when its orbit carries it through the anomaly. Astronauts aboard are informed. Certain sensitive instruments are powered down or placed in protective modes. This has been standard operational procedure since the station began continuous habitation. The anomaly is not new. It has been documented in satellite data since the 1950s. What is new is what is happening to it. The anomaly is expanding in geographic area and deepening in its minimum intensity. It is growing. It is also showing signs of developing a second center of weakness, a split into two separate low-intensity regions, which represents a structural change in the anomaly's character that researchers find significant. The cause is tied directly to what is happening in the outer core beneath that specific region of the planet. Under the South Atlantic and the southern tip of Africa, there is an unusual structure in the outer core called a low-velocity zone, a region where liquid iron moves differently from the surrounding material, with properties suggesting reversed magnetic polarity. Some researchers believe this zone represents a patch of the outer core where the local magnetic field alignment is opposite to the globally dominant direction. The interaction between this reversed patch and the overall outward field produces the surface weakness above it. The reversed patch is not static. It is growing, and in the process, it is strengthening the anomaly above it and extending its geographic reach. This connects back to the rotation story in a way that requires careful attention because it is not immediately obvious. Changes in outer core flow patterns affect the magnetic field. Changes in the magnetic field affect the electromagnetic coupling between the outer core and the mantle above it. Changes in that coupling affect the transfer of angular momentum between the core system and the surface. The South Atlantic anomaly is not merely a radiation hazard for satellites and space travelers. It is a visible, measurable symptom of changes in the outer core that share an origin with the rotation anomaly this account began by describing. The two phenomena are not the same event, but they share a common source: shifts in the behavior of the liquid iron ocean 2,000 miles down, and they are evolving together. The last time Earth's magnetic field weakened significantly on a global scale, something more consequential followed. The field reversed entirely. North became south. South became north. The rock record shows it has happened hundreds of times across Earth's history, and the current state of the field, its ongoing gradual weakening, its regional anomalies, its South Atlantic structures making at least some researchers ask whether we are watching the early stages of another one. Magnetic field reversals are among the stranger confirmed facts in all of Earth science. The polarity of the planet's field has flipped completely and globally roughly every 200,000 to 300,000 years on average, though the timing is highly irregular, with gaps between reversals ranging from tens of thousands to tens of millions of years. The last full reversal, called the Brunhes-Matuyama reversal, occurred approximately 780,000 years ago. By average statistical expectation alone, we are overdue. That statement requires careful framing. The word overdue carries specific meaning in everyday language that does not transfer cleanly to geological processes. Reversals are not like trains running on a schedule. Being past the average interval tells us almost nothing about when the next one will happen. The system has no memory of time elapsed. A reversal could occur tomorrow, or could be hundreds of thousands of years away, and the current data would be consistent with either possibility. What the data can tell us is something different. During a reversal, the field does not simply flip instantaneously from one polarity to the other. The transition takes thousands of years. During that transition, the field weakens substantially, dropping, in some reconstructions of past reversals, to perhaps 10 to 20% of its normal global strength. The protective bubble that deflects charged particles from the sun is greatly reduced across most of the planet during that extended transition period. The consequences are not extinction level. Life has survived every reversal in Earth's history. But survived is doing some significant work in that sentence, and the details matter. Increased radiation reaching the surface would measurably elevate cancer rates in populations without the current infrastructure protections we take for granted. It would intensify damage to satellites and to power grid infrastructure that depends on satellites for synchronization. It would affect the navigation systems of migratory animals, birds, sea turtles, certain fish that rely on magnetic sensing as a primary orientation mechanism. Atmospheric chemistry could be altered by the increased particle flux penetrating to lower altitudes. These are not catastrophic in isolation, but they compound. Here's the connection that closes the loop between the magnetic field and the rotation story. The geodynamo that generates the magnetic field is powered by the same convective flows in the outer core that interact with the rotation of the planet above it. The field and the rotation are not independent systems. They are physically coupled through the outer core's behavior. When the outer core's flow patterns change in ways that weaken the field, those same changes alter the electromagnetic torque on the mantle. That torque affects the rotation rate of the crust above. A weakening field and a changing rotation rate are not two separate stories. They are two different visible symptoms of one underlying story happening in the outer core. Researchers who study the paleomagnetic record, the preserved history of past magnetic behavior embedded in ancient rocks and seafloor sediments, have found correlations between periods of field weakness and anomalies in climate and geological records that appear alongside them in time. The relationships are complex and not fully understood. Causation is difficult to establish from the geological record, but the correlations are persistent enough across multiple episodes to warrant continued investigation. What is particularly relevant to the present moment is this. The current rate of global field weakening is faster than the average background rate measured during non-reversal periods in the geological record. The global field intensity has declined by roughly 9% since systematic measurements began in the early 19th century. 9% in approximately 180 years represents a significant rate of change by any reasonable geological standard. Whether this represents the early stages of a reversal, a temporary excursion that will correct without completing a full flip, or something else entirely is not determinable from the current data. The scientific community is genuinely uncertain. What can be stated with confidence is that the field is behaving differently today than it was 200 years ago. The outer core driving it is behaving differently than it was 2 decades ago. The surface is rotating faster than it has in 50 years of precise measurement. These are all real, confirmed, independently verified measurements. The question of how they are connected, and what their combined trajectory implies for the century ahead, is one that geophysicists are working with increasing urgency to answer. Part of that work involves reading the only archive that covers timescales long enough to provide context for what is currently observed. That archive is the geological record. And the geological record is stored in rock, in ancient lava flows, in seafloor sediments, in coral skeletons, and in the layered mud of ancient tidal flats that recorded the rhythm of the planet's spin hundreds of millions of years before the first instrument was ever built. There is a library inside the planet. Not books, not symbols, physical records pressed into cooling rock. At the moment, it's solidified and never altered afterward. A record of the magnetic field's past, preserved with extraordinary fidelity in microscopic crystals of iron-bearing. Minerals. When lava erupts and flows across the surface, cooling and hardening into basalt, tiny magnetic minerals in the rock align themselves to the direction and intensity of Earth's magnetic field at that exact moment of cooling. They orient themselves like compass needles, pointing toward the magnetic pole as it exists right then. As the rock hardens around them, they are frozen in place. The record they carry can survive for hundreds of millions of years, through erosion, through burial, through the slow movements of tectonic plates, without the magnetic signature being significantly altered. Using this property, paleomagnetists have assembled a history of Earth's magnetic field extending back more than 4 billion years. The magnetic record is not the only information preserved in ancient rock. Thin layers in seafloor sediments record cyclic variations in deposition tied to the number of days in a year, because the tidal forces that drive those cycles are linked to Earth's rotation rate. Ancient tidal rhythmites, sequences of sediment deposited by tides in shallow coastal environments, preserve a count of tidal cycles per year, which is directly related to how fast the planet was spinning at the time of deposition. Ancient coral is among the most useful of these natural archives. Coral grows in daily and annual increments that can be read like growth rings in a tree. Coral specimens from approximately 400 million years ago, analyzed beginning in the 1960s, showed approximately 400 growth rings per year. Since the length of a year is set by Earth's orbit and does not change, more days in a year mean shorter days. The planet was spinning measurably faster. The data from even older specimens is consistent with the trend. Tidal rhythmites from approximately 620 million years ago suggest Earth had a day of roughly 21 to 22 hours. The planet has been slowing for hundreds of millions of years. The direction of the trend is confirmed across multiple independent lines of evidence. But within that long deceleration, there are variations. Periods where the rate of slowing changed, periods where small reversals of the trend occurred. The record shows that Earth's rotation is not a simple one-way street decelerating at a constant rate. It fluctuates on timescales from decades to millions of years, driven by the interplay of tidal braking, core dynamics, and mass redistribution. The current anomaly, the acceleration observed since 2016, is not without geological precedent. It is just without precedent in the modern instrumental era. The paleomagnetic record also captures past reversals in the seafloor with remarkable clarity. As new oceanic crust forms at mid-ocean ridges where tectonic plates spread apart and magma wells up from below the fresh basalt, records the magnetic field polarity at the moment of cooling. Alternating stripes of normal and reversed polarity extend outward from mid-ocean ridges in both directions, like a long recording of the field's history printed in stone and slowly spreading across the ocean floor. The width of each stripe corresponds to how long the field maintained that polarity before reversing. The record is detailed enough to identify not only full reversals, but also shorter events called geomagnetic excursions, episodes where the field began to shift and weaken, but then recovered without completing a full reversal. The last Champ excursion, roughly 42,000 years ago, is the most thoroughly studied of these events. During the last camp, global field intensity dropped dramatically over several centuries, reaching perhaps 5 to 10% of its normal value, before recovering over several thousand years to approximately normal strength. The transition period was brief by geological standards, but lasted long enough to leave signatures in multiple independent archives. Cave records specifically, the records of cosmogenic isotopes, like beryllium, 10, and carbon, 14, that are produced when cosmic rays penetrate deeper into the atmosphere during periods of reduced magnetic protection, show elevated values during the last camp. Ice cores from Antarctica and Greenland show the same signal. Tree rings preserve the carbon, 14 signature as well. Some researchers have connected the last Champ excursion to periods of climate disruption and to episodes of megafauna extinction that appear in the fossil record from roughly the same period, though the causal chain is contested, and the coincidence of timing may be partial rather than exact. The significance of the last Champ for the present is not that another one is imminent. The significance is that these events are real, that they have happened within the time frame of modern human ancestors, and that they leave detectable physical signatures across multiple environmental systems simultaneously. The current state of the magnetic field, its regional weakness in the South Atlantic, its measurable global decline, its shifting pole positions, has measurable structural similarities to early-stage excursions preserved in the geological record. That observation is not a prediction. The field has shown similar features before without proceeding to a full excursion or reversal. But the similarity is noted in the scientific literature, and it is part of why the researchers monitoring the field most carefully are watching the current data with particular attention. The geological record does not predict the future, but it defines the range of what is physically possible. It shows what Earth has been through, and it shows, repeatedly, that the extremes of Earth's behavior are more extreme than intuition built on human timescales would suggest. The rocks also tell us something about the last time Earth's rotation was behaving the way it is currently behaving. What was happening on the surface during those periods was not calm. And that comparison between the current anomaly and its nearest geological analogs is where the picture becomes most instructive and, in certain ways, most sobering. Determining the precise rotation rate of Earth at a specific point in the geological deep past is not a simple calculation. The proxy measurements have their own uncertainties. The causes of past speed changes are not always identifiable with certainty from the evidence left behind. But researchers have assembled enough of a coherent picture to say something meaningful about comparable events and their broader context. The last period in Earth's reasonably recent geological history, when rotation accelerated on a scale comparable to what is now being measured, was almost certainly during the end of the last glacial maximum, the period roughly 15,000 to 20,000 years ago, when the enormous ice sheets that had covered large portions of the northern hemisphere began their final, rapid retreat. As those ice sheets collapsed, massive quantities of meltwater entered the ocean, redistributing planetary mass in the same ways described earlier in connection with the current ice loss. The crust freed from the enormous weight of the ice began to rebound upward, a process called isostatic rebound that continues even today in regions like Scandinavia and Hudson Bay, where the land is still rising measurably every year, thousands of years after the ice that pressed it down has vanished. The redistribution of mass from the melting ice affected the planet's moment of inertia, and therefore its rotation rate. The geophysical signatures of that deglaciation are preserved in the geological record with enough resolution to be compared to what instruments are measuring today. The parallel to the present is imperfect, but instructive. We are not in a glacial retreat driven by orbital, forcing the slow changes in Earth's orbit and axial tilt that set the pace of ice ages over tens of thousands of years. We are in a different kind of deglaciation, one driven by atmospheric warming over decades. The timescale is considerably faster. The geographic pattern of ice loss is different, but the fundamental physical mechanism is comparable. Mass that was concentrated near the poles is moving toward lower latitudes. The crust is adjusting. The rotation is responding. What the geological record of the last glacial retreat tells us is that these mass redistribution events do not produce smooth, gradual, linear changes in rotation. They produce irregular, episodic shifts, stepwise changes, as different ice sheets respond at different times, as meltwater pulses occur in concentrated episodes rather than steady flows, and as the solid Earth responds to unloading with its own delays and regional variations in rebound rate. During the deglaciation of the last ice age, there were periods where sea level rose by several meters within just a few centuries, not the gradual millimeter by millimeter rise of steady conditions, but rapid, episodic surges as particular ice sheet sections became unstable. Meltwater pulse 1A, identified in the sea level record at approximately 14,500 years ago, raised global sea levels by roughly 14 to 18 meters in a span of perhaps 300 to 500 years. The redistribution of that volume of water in that time frame was large enough to leave a detectable signature in rotation data reconstructed from tidal rhythmites and other proxy records. There is a volcanic dimension to this story that does not always receive the attention it deserves. During periods of rapid deglaciation, volcanic activity tends to increase. The mechanism is pressure release. Ice sheets are extraordinarily heavy. The West Antarctic ice sheet, for reference, weighs enough to depress the bedrock beneath it by kilometers. When that weight is removed, the crustal pressure drops. The mantle rock beneath, which was already near its melting point, due to geothermal heat, prevented from melting only by the immense pressure, holding it in its solid state, finds that the pressure has been reduced. Rock that was barely solid becomes melt, and that melt rises. The result is increased volcanism in and around deglaciated regions. Iceland is among the most intensively studied examples of this relationship. Research on Icelandic volcanic history shows substantially elevated eruption rates during and after the last deglaciation, with the relationship between ice removal and volcanic response tracked across thousands of years. The same physical mechanism is expected to operate during the current period of ice loss, and there is early observational evidence that it is beginning to do so. Monitoring in Iceland, in Greenland's peripheral volcanic zones, and in certain regions of West Antarctica, has detected subtle but measurable changes in subsurface pressure and microseismic activity that are consistent with the beginning of a deglaciation-driven volcanic response. That response has its own timeline centuries, not decades, and its own potential to interact with the rotation system as volcanic activity distributes mass across the crust. The picture that emerges from the geological record is not one of catastrophe occurring on human timescales. It is a picture of interconnected changes, each driving the next, each adding to a cumulative shift that takes centuries to fully express itself in the observational record. What concerns the researchers watching the present data most carefully is not any single measurement in isolation. It is the number of systems changing simultaneously. And what happens when all those signals are laid on top of each other when the core rotation anomaly, the ice redistribution, the magnetic field weakening, and the atmospheric and ocean changes are plotted on a common timeline is the most unsettling part of this entire account. But before that synthesis, there is one more thread to pull. The connection that the geological record hints at most strongly. The relationship between faster rotation and the deep Earth's response in the form of seismic and volcanic activity is also the connection that is most difficult to communicate without either understating the science or stepping beyond what the data currently supports. The data does support something. The mechanism is physically grounded. The correlation exists in the historical record. Whether it will express itself in the present remains genuinely uncertain, but it is part of the picture, and it belongs in any honest account of where the story currently stands. In 2017, a paper published in Geophysical Research Letters made a claim that drew immediate and sustained attention from both scientists and the wider public. The researchers had analyzed historical earthquake records going back more than a century, a dataset spanning over 100 years of global seismographic observation, covering thousands of significant events across every tectonic region on Earth. What they found in that dataset was a correlation that, once seen, was difficult to dismiss. Periods, when Earth's rotation slowed even slightly. Periods, when the planet was decelerating fractionally relative to its recent average, were followed, roughly 5 years later, by measurable increases in the number of major earthquakes. Not minor tremors. The researchers were looking at events measuring magnitude 7 or above earthquakes, capable of destroying cities, collapsing infrastructure, and generating tsunamis. The correlation was statistically significant. The 5-year lag between the rotational signal and the seismic response was consistent across multiple episodes in the historical record. And the mechanism the researchers proposed was not speculative. It was physically grounded in what we know about how the planet is structured. Here is the mechanism. When Earth's rotation slows even fractionally, the equatorial bulge, the slight thickening of the planet at its middle, caused by the centrifugal effect of rotation pushing mass outward, adjusts. It has to. The rotation rate is lower, so the centrifugal effect is slightly weaker, so the equatorial bulge decreases very slightly. The crust at lower latitudes shifts inward toward the rotation axis by a tiny but measurable amount. That inward movement applies horizontal compressive stress to tectonic plates at tropical and subtropical latitudes. Faults that were already under stress, already close to the threshold of failure from the slow, relentless pressure of plate tectonics, can be nudged over that threshold by the additional stress. The same logic runs in reverse when rotation speeds up. The equatorial bulge increases slightly as the centrifugal effect strengthens. The crust at the equator stretches outward. Faults under extensional tension, rather than compression, can be triggered. The types of earthquakes most likely to be influenced differ between the acceleration and deceleration scenarios, because different fault geometries respond to different stress orientations. But the fundamental triggering mechanism is the same in both cases. Rotational change applying measurable, if small, additional stress to a crust already straining under the enormous forces of plate tectonics. The paper's authors noted explicitly that the global seismic system had recently exited a period of slowing and entered one of acceleration. By the logic of their 5-year lag model, the mid-2020s represented a period warranting particular attention from seismologists monitoring global activity patterns. That prediction has not been definitively confirmed or refuted as of the time these words were written. Earthquake prediction is one of the hardest and most contested problems in all of Earth science. Most seismologists are appropriately cautious about any strong claims connecting rotation to seismic activity, and the correlation identified in the study, however statistically compelling, has not yet been confirmed through fully independent physical modeling to the point where the broader community considers it established. What is considerably less contested is the volcanic dimension of the same relationship. Rotation rate changes affect the behavior of fluids beneath the crust, and the outer core is not the only such fluid. The upper mantle contains partially molten rock in certain regions, particularly beneath mid-ocean ridges and in the mantle wedges above subducting tectonic plates. Changes in the rotational stress, applied to the crust and upper mantle, can affect where and how that partially molten material moves, which fissures it enters, which volcanic conduits it pressurizes, which eruptive systems it activates. A separate study, examining global volcanic eruption rates across the last 500 years, found a weak but statistically detectable correlation between periods of rotation anomaly and subsequent volcanic episodes, again, with a lag of years to decades between the rotational signal and the surface response. The lag matters enormously for interpreting the current situation. It means that whatever effects the current acceleration is exerting on the geological system beneath our feet, those effects may not be fully expressed for years or decades to come. The slow, accumulating consequences of a rotational shift propagate through the Earth's layered interior on timescales that dwarf the news cycle, the political cycle, even the human lifetime. We are living through a rotational event whose full geological response is still in transit, still traveling upward through the layers, still approaching the surface. This is the part of the story that researchers find genuinely difficult to communicate without falling into one of two traps, either understating the significance of what the data shows, or veering into language that suggests catastrophe is imminent when the science does not support that framing. The planet is not ending, the systems are not collapsing, but the Earth is under more simultaneous, correlated geophysical stress right now than at any point in the modern instrumental record, and the appropriate response to that observation is not dismissal, it is attention. Sustained, serious, scientifically rigorous attention, which is precisely what the researchers currently working on these questions are providing, often with funding that is inadequate to the scale of the questions being asked. None of the individual signals, taken in isolation, constitutes a crisis. The rotation anomaly alone would be a footnote in the geophysical literature. The magnetic field weakening alone would be a subject of ongoing monitoring with appropriate concern but no alarm. The ice loss alone would be a climate story with well-understood physical consequences. But combined operating on the same geological system simultaneously, interacting through feedback loops that amplify each other's effects, they represent a forcing situation that the established models, calibrated on historical data from periods when the forces were smaller and less correlated, cannot reliably project forward. There is one more member of this ensemble that has not yet been fully addressed. The atmosphere itself, the layer of gas that wraps this planet, weighing roughly 5 quintillion kilograms in total, moving constantly in patterns that express themselves as weather at human scale, and as something considerably larger at planetary scale, is not a passive bystander in the rotation story. It is an active participant, and it is changing in ways that add its own signature to the rotation budget at the same time everything else is shifting. The atmosphere is not light. It does not float passively above the surface like steam above hot water. It is a layer of gas with real mass, comparable in total to the mass of a substantial mountain range distributed across the entire surface of the planet. And that mass moves. When it moves, it pushes. When it pushes against a rotating surface, it exerts a torque. This is not a theoretical coupling. It is measured directly and continuously. Meteorologists and geodesists have spent decades comparing atmospheric angular momentum data derived from global wind measurements and atmospheric pressure observations with Earth rotation data derived from atomic clocks, radio telescope networks. The correspondence is remarkable. When the atmosphere gains angular momentum, typically through the development and strengthening of large-scale wind systems at certain latitudes, the solid Earth slows down fractionally to conserve the total angular momentum of the combined system. When the atmosphere loses angular momentum, when those wind systems weaken or shift, the solid Earth speeds up correspondingly. The two systems are coupled through friction at the surface, and they continuously exchange rotational energy in response to atmospheric dynamics. The dominant signal in this exchange is seasonal. The winter hemisphere develops stronger west-to-east jet streams than the summer hemisphere. Those jet streams carry angular momentum westward relative to the surface. The solid Earth responds by rotating slightly slower during the boreal winter than during the boreal summer. The effect is small, on the order of 1 millisecond variation across the year, but it is clearly measurable with modern instruments, and it was one of the first atmospheric rotation connections to be quantitatively established. There are also non-seasonal components of this exchange. and some of them are considerably larger than the seasonal signal. El Niño events are the most significant non-seasonal driver. During a strong El Niño, trade winds in the tropical Pacific weaken substantially. This weakening represents a reduction in atmospheric angular momentum. The solid Earth absorbs that angular momentum and spins slightly faster. The relationship has been documented across multiple El Niño events with enough consistency to be considered one of the more reliable rotation-atmosphere connections in the observational record. Strong El Niño events in 1982 to 1983, in 1997 to 1998, and in 2015 to 2016, each produced measurable rotation anomalies that appeared in the precise clock data within months of the atmospheric changes. The 2015 to 2016 El Niño was one of the strongest ever recorded in the modern instrumental era. Its timing coincides closely with the beginning of the surface acceleration trend that researchers have been tracking with increasing attention since. That coincidence of timing is not necessarily causal in a simple, direct way. The acceleration has persisted well beyond the influence of that particular El Niño, and its magnitude is larger than El Niño alone can account for. But El Niño may have contributed to the initial departure from baseline rotational behavior that the core dynamics, the ice redistribution, and other longer-acting forces subsequently extended and amplified. Here is where the atmospheric contribution becomes structurally important to the overall picture. The atmosphere is not just a passive channel through which rotational energy flows. It responds to changes in the ocean. It responds to changes in ice coverage and to the albedo shifts that accompany ice loss. It responds to changes in the magnetic field through effects on ionospheric circulation and on the chemistry of the upper atmosphere. These connections mean that as other systems in this account evolve, the atmosphere evolves with them, and its rotational contribution evolves in turn. The jet stream, in particular, has undergone documented changes over the past 2 decades that are linked to Arctic warming and the reduction in the temperature gradient between the Arctic and mid-latitude regions. A steeper temperature gradient drives a stronger, more consistently westward jet stream. A weaker gradient, as the Arctic warms faster than lower latitudes, drives a slower, more meridional jet stream that wanders further north and south. That wandering jet stream redistributes atmospheric angular momentum differently across latitudes than a strong zonal jet stream does. The rotational signature is different. The coupling between the atmosphere and the ocean beneath it is different. And the feedback between that changed atmospheric pattern and the ice loss that partially caused it runs in a direction that does not tend toward stabilization. The stratospheric polar vortex, the column of rapidly rotating cold air that sits over the Arctic through the winter months, is also connected to this picture. When the polar vortex weakens and breaks down, which it has been doing with increasing frequency and intensity in recent decades, it allows cold Arctic air to spill far into lower latitudes. Those cold air intrusions represent sudden redistributions of atmospheric mass from high latitudes toward lower ones. Each such event is brief, but each one carries a rotational pulse, a small rapid perturbation in the atmospheric angular momentum budget that shows up in the rotation data days to weeks later. The atmosphere, viewed at the level that matters for understanding Earth's rotation budget, is not just a complicating factor. It is an integrating factor, a system that receives physical signals from ice loss, ocean warming, and core-driven magnetic changes, and rebroadcasts those signals as mechanical forces acting on the crust below. Every change in the atmospheric circulation pattern changes its contribution to the rotation budget. And the atmospheric circulation pattern is changing faster now in more directions, over more geographic regions, with greater persistence and larger amplitude than at any point in the modern observational record. If you have ever moved your hand quickly through water, you have felt the drag. The water resists. The faster the motion, the more resistance it offers. The principle at planetary scale is the same, scaled up to an ocean that covers more than 70% of the Earth's surface to an average depth of roughly 2.5 miles. Earth's oceans interact with the rotating solid Earth through friction at the ocean floor and through pressure variations across underwater topographic features, ridges, seamounts, the great mid-ocean mountain chains. That interaction creates a braking effect. It is small compared to tidal friction from the moon, but it is real, it is measurable, and it is changing along with everything else. Ocean angular momentum. The rotational energy carried by ocean currents is tracked continuously by teams of physical oceanographers and geodesists working in coordination. The total angular momentum of the Earth-ocean atmosphere system must be conserved. When ocean currents strengthen in ways that carry more angular momentum in one direction, the solid Earth responds by rotating fractionally more slowly. When currents weaken, the solid Earth speeds up. The exchange is continuous, bidirectional, and sensitive to any large-scale change in ocean circulation. The deep ocean circulation system, the global network of currents driven by temperature and salinity differences, slowly circulating water through all the world's ocean basins over timescales of hundreds to thousands of years is changing. The Atlantic meridional overturning circulation, the component of this system that carries warm surface water northward along the eastern coast of North America and toward Western Europe, before sinking as it cools and returning southward as a deep cold current, has been weakening. Multiple independent datasets, including sediment records from the ocean floor, satellite altimetry data, and direct current measurements at carefully chosen locations in the Atlantic, all point to the same conclusion. The circulation is operating more slowly than it was several decades ago. Some analyses, using sediment-based proxies that extend the record back over centuries, suggest the circulation may now be at its weakest point in more than 1,000 years. The slowdown has implications that range from European climate patterns to tropical rainfall distribution to sea level along the northeastern coast of North America. But it also carries a rotational signature. The circulation transports angular momentum through the ocean basins in a specific geographic pattern. When that pattern changes, as it is changing now, the distribution of ocean angular momentum changes with it. The net rotational effect of a weakened Atlantic circulation is not straightforward to calculate, because it depends on the details of how other ocean systems compensate. But the directional changes are real and are being incorporated into the increasingly sophisticated models that attempt to project the rotation budget forward. There is a thermodynamic dimension to the ocean's rotational contribution that operates through a different pathway. Warmer ocean water is less dense than cold water. A warming upper ocean therefore occupies more volume than it did when it was cooler. This is called thermal expansion, and it is one of the two primary drivers of sea level rise, alongside the addition of water from melting ice. As the upper ocean warms and the thermocline, the boundary layer between warm surface water and cold deep water, deepens, the vertical structure of the ocean changes in a way that alters where angular momentum resides within the water column and how it couples to the rotation of the solid Earth below. There is also a storm dimension. Warmer ocean surface temperatures supply more energy to tropical storms. A major hurricane or typhoon is a large rotating atmospheric structure with significant angular momentum. The formation, intensification, and decay of these systems redistributes angular momentum between the atmosphere and ocean in ways that are individually small but collectively significant when summed across an ocean basin over a full storm season. An ocean that generates more intense storms more frequently is an ocean that perturbs the rotation budget more often and over larger geographic areas. The cumulative effect of all these oceans changes the circulation slowdown, the thermal expansion, the changed angular momentum distribution. The increased storm activity is not yet large enough to be the dominant driver of the surface acceleration. That is the central subject of this account. But it is real, it is measurable, it is growing, and it is changing in the same decade as everything else, driven in significant part by the same underlying conditions, and interacting with the atmospheric changes described earlier in ways that do not simplify the picture. Among the researchers watching Earth's rotation data most carefully, there is a legitimate scientific division about how to interpret what is being observed. It is worth laying out both sides of this disagreement clearly, because the disagreement is not between careful scientists and careless ones. It is between careful scientists who weight the evidence differently and draw different conclusions from genuinely ambiguous data. The first position held by a significant portion of the geophysical community is that the current surface acceleration is a transient phenomenon, a fluctuation near the high end of a natural cycle that will be followed, in time, by a return to the long-term deceleration trend. The argument is grounded in the nature of Earth's rotation variability. The planet's rotation has always oscillated on multiple timescales simultaneously. There are decadal fluctuations driven by core-mantle angular momentum exchange. There are interannual fluctuations driven by atmospheric and ocean cycles. There are seasonal fluctuations tied to the redistribution of atmospheric mass. These oscillations are real, they are well documented, and they do not all move in the same direction at the same time. On this interpretation, the current surface acceleration represents a phase of these overlapping cycles during which several components happen to align in the speed-up direction simultaneously. The acceleration is unusual in its magnitude, producing some of the shortest days ever measured with modern instruments, but not necessarily unusual in its fundamental nature. Given sufficient time, the cycles will move out of alignment. Some will begin pulling in the deceleration direction. The trend will eventually reverse. The geological record supports this interpretation in the sense that similar episodes of short-term acceleration have appeared before in the proxy data and have all been followed by a return toward the long-term mean. The counterargument, made with equal care by a different group of researchers, identifies at least two ways in which the current situation is structurally different from past fluctuations differences that matter for projecting what comes next. The first structural difference is that some of the current drivers are not cyclical. Ice sheet loss is not an oscillation. It is not a fluctuation that will correct itself when the cycle completes. It is a one-way trend that is accelerating. The mass redistribution it causes does not reverse when an El Niño ends, or when a core flow pattern shifts back. It accumulates. Each year of net ice loss adds to the cumulative change in the planet's moment of inertia, and the rotational effect of that accumulation compounds over time. A planetary system facing an accelerating, non-reversing external forcing is not simply a system in a different phase of a familiar cycle. It is operating under conditions that have no precise historical analog in the instrumental record. The second structural difference is the inner core's apparent behavioral shift. If the reversal in inner core rotation is real, and represents a genuine change in the dynamic regime of the planet's interior, rather than a transient fluctuation in what was already a slowly varying system, then the coupling between the core and the surface is operating differently than it has during the period for which we have detailed observational data. A core that has changed its rotation direction is not a pendulum at a different point in its swing. It is a pendulum that has begun swinging in a different plane. The implications for the surface rotation are not well constrained by the historical record, because the historical record does not contain a clear analog for this specific change. The honest scientific answer, as of the current state of knowledge, is that both interpretations have valid supporting evidence, and neither has sufficient data to be confirmed to the exclusion of the other. What can be said with confidence is that the range of possible future trajectories for Earth's rotation is wider today than it was 20 years ago. The system is less predictable, not because our instruments have gotten worse, but because the forcing conditions are further from the range of the historical record that calibrated the models. That widening uncertainty has consequences that are not merely academic. The systems that depend on Earth's rotation for their calibration timekeeping infrastructure, satellite navigation networks, power grid synchronization, financial market timestamps were designed with safety margins established by decades of experience, operating on a planet that behaved within a well-characterized range. If the planet moves persistently outside that range, in either direction, those margins become progressively less adequate. The gap between what the systems were designed for and what the planet is actually doing widens. Engineers working closest to these systems know this and are actively working on it. But engineering responses to unexpected conditions take time. Standards bodies move slowly. Infrastructure replacement is expensive and politically difficult. The systems that would feel the stress first, the ones with the least redundancy and the tightest tolerances, are not necessarily the ones with the most institutional capacity to adapt quickly. There is a number that appears repeatedly in the technical literature on Earth rotation and its implications for timekeeping infrastructure. 1 minute. Not 1 second, 1 minute. That is the maximum gap between atomic time and Earth time that international agreements permit before a correction mechanism other than the abandoned leap second must be applied. 1 minute sounds large. At the rates of divergence observed in recent years, it would take roughly a century to accumulate that gap at current rates. But current rates are not guaranteed to continue, and infrastructure plans are written on 20 to 40-year horizons not century-scale ones. If the acceleration continues, the gap grows faster. If the planet's rotation undergoes a rapid deceleration in the other direction, as would happen if the core angular momentum transfer completes and reverses, or if a large meltwater pulse rapidly redistributes ocean mass, the gap grows faster still, just in the opposite direction. The tipping point for infrastructure is not the gap reaching a specific value. The tipping point is the rate at which the gap approaches its limit, changing faster than the systems monitoring and correcting for it were designed to accommodate. There is a separate and more immediate tipping point hidden in the physical system itself, one that does not operate on century timescales. Researchers studying the interaction between ice loss, sea level rise, and coastal glacial dynamics have identified configurations within the current ice sheet system where feedback becomes self-reinforcing, in a way that is by definition difficult to detect before it is crossed. The mechanism works like this. As an ice sheet loses mass along its margins, the bedrock beneath it rebounds upwards slowly, but measurably. In some geometries, that rebound changes the gradient of the ice sheet surface in a way that alters how meltwater drains. In certain configurations, most notably within the geometry of the West Antarctic ice sheet, which sits on a bed that slopes inland, meaning that the ice sheet becomes less stable as it retreats. Rather than more, a threshold of ice loss triggers a drainage and flow reorganization that accelerates further loss independent of whatever initially caused the melting. The system tips into a faster loss regime and cannot easily recover. This is the kind of tipping point that is extraordinarily difficult to identify from the outside before it has been crossed. The warning signs are subtle. The transition from stable to accelerating may unfold over decades in ways that are individually within the range of year-to-year variability. By the time the acceleration becomes unmistakable, the system has already committed to a trajectory that cannot be reversed on any timescale, relevant to the infrastructure that depends on the rotation budget remaining within a manageable range. The rotation connection is that a rapid, large-scale meltwater pulse, the kind that has appeared in the geological record as sea level events measurable in meters over centuries, produces a rotation signal that is both large in magnitude and relatively abrupt in timing. The existing correction infrastructure was not designed for abrupt, large signals. It was designed for the gradual, predictable drift that characterized the last several decades of operation. There is one more threshold identified in the modeling literature that deserves mention here, because it connects directly to the core dynamics that started this account. Researchers studying the behavior of the outer core under different boundary conditions have found, in certain classes of geodynamo models, flow patterns that can shift between two distinct stable states. Much the way a physical system in mechanics can rest in either of two equilibrium configurations, stable in each, but requiring only a modest perturbation in exactly the right direction to flip from one to the other. The current flow pattern in the outer core, which appears to be associated with the observed surface acceleration through the coupling mechanisms described earlier, may represent one such stable state. If the system transitions to the other stable state, the rotational effect at the surface could reverse relatively rapidly. A planet that has been accelerating for a decade could begin decelerating sharply over a period of years to decades. The gap between atomic time and Earth time would then accumulate in the opposite direction at a rate that the current correction infrastructure, recalibrated for a gradually accelerating planet, would struggle to manage. Whether we are anywhere near any of these thresholds is genuinely unknown. The models that identify them are sophisticated but imperfect. The observations that would distinguish proximity to a threshold from comfortable distance from it are precisely the observations that are hardest to make with confidence, because the signals of approaching tipping points are often indistinguishable from ordinary variability until after the threshold has been crossed. That is, in a sense, the definition of a tipping point. What can be said is that the systems that would be affected by crossing any of these thresholds are already operating under increasing stress from the gradual accumulation of the anomalies described in this account. There is a concept in complex system science called correlated forcing. It describes what happens when a system, any system, from a bridge to a biological population to a planet, is subjected simultaneously to multiple independent pressures that happen to be pointing in the same direction. A single pressure on a complex system is manageable. The system has evolved responses to single pressures Its redundancies and feedback mechanisms are tuned to handle perturbations that come one at a time. But when multiple pressures arrive together, when they reinforce each other through feedback, when the response to one creates conditions that amplify another, the behavior of the system enters territory that its historical responses cannot reliably predict. Earth is now in that territory. The rotation is anomalous, accelerating beyond any value in the 50-year modern instrumental record. The inner core has shifted its rotational behavior in a way that has no clear precedent in the observational data. The outer core's circulation pattern has changed, producing both a rotation signal and a magnetic field signal. The magnetic field has weakened regionally in the South Atlantic anomaly and globally at a rate measurably faster than background. The ice sheets are losing mass at rates that were not projected under median climate scenarios to occur until later in this century. That meltwater redistribution is physically shifting the planet's spin axis and altering its moment of inertia in real time. The oceans are warming, expanding thermally, and changing their large-scale circulation in ways that carry rotational signatures. The atmosphere is responding to all of the above, and feeding its own angular momentum changes back into the rotation budget. The geological indicators, the subsurface pressure changes in deglaciated regions, the microseismic signals in Iceland and West Antarctica, point toward a slow-building volcanic and tectonic response that is in its early stages. Each of these is a documented, published, independently monitored phenomenon. Each has its own research community, its own funding streams, its own journals and conferences. What is less common, and what makes the current moment distinctive in the history of Earth science, is the attempt to look at all of them simultaneously and ask what they tell us together, that they cannot tell us separately. When researchers have done that, what they find is not coincidence. The changes are not independent, they are coupled. The weakening magnetic field reflects outer core changes that also affect rotation. The ice loss affects both the rotation and the ocean circulation patterns that affect the geodynamo's excitation. The atmospheric shifts affect the rotation and also affect where precipitation falls, which affects ice accumulation rates at the poles. The ocean circulation changes affect where heat is distributed, which affects ice shelf stability, which feeds back into the ice loss rate. These are not metaphorical connections or narrative conveniences. They are physical couplings with measurable signatures in the observational record. The result is a system that is moving in multiple dimensions simultaneously, where motion in each dimension amplifies motion in the others. The word used in the technical literature for this situation is non-stationary. The statistical properties of the system are changing. The mean is shifting. The variance is increasing. The historical record is becoming a progressively less reliable guide to future behavior, not because the physics has changed, but because the forcing conditions are departing from the range within which the historical record was assembled. This is not a cause for paralysis. Science has operated in non-stationary environments before and has adapted to them. Monitoring networks are expanding. Models are being revised to incorporate the new observations. The scientific community is aware, engaged, and working on these questions with more resources and more data than any previous generation had access to. But awareness requires honesty about where the uncertainty lies and how large it is. And the honest acknowledgement from the researchers, closest to the data, is that the uncertainty is larger today than it was 10 years ago, not smaller. More monitoring has produced more evidence of change. Better models have produced better understanding of the mechanisms. And better understanding of the mechanisms has revealed how tightly coupled the systems are, which means how readily a change in one can drive changes in others in ways that compound and propagate. 3 distinct theoretical frameworks have emerged from the scientific literature over the past decade, each offering a different interpretation of the current anomaly and a different projection of what follows. They are not mutually exclusive. All 3 could be partially correct simultaneously, but they lead to meaningfully different predictions about the planet's trajectory over the next several decades. And the data available at present is not sufficient to choose definitively between them. The first is the core-driven model. This framework holds that the primary driver of the current surface acceleration is the change in inner core rotation and its cascading effect on outer core circulation. In this view, the apparent reversal of the inner core's rotation is real, and the angular momentum transferred upward through the layers as the inner core decelerated is the dominant signal in the rotation data. The surface acceleration is a delayed echo of a deep structural change that began in the early 2000s and whose effects have been propagating outward ever since. The prediction from this framework is that the acceleration will continue until the angular momentum transfer is substantially complete, then stabilize or reverse as the system works toward a new rotational equilibrium. The timescale for this stabilization is estimated at decades. The magnitude of any subsequent reversal, if one occurs, would be comparable to the current acceleration. The second is the ice-atmosphere coupling model. This framework holds that the dominant driver of the acceleration is the combination of polar ice loss and its effect on atmospheric circulation, particularly the destabilization of the polar vortex and the shift in jet stream. Behavior described earlier in this account. Ice loss reduces the temperature gradient between the Arctic and mid-latitudes. That gradient drives the jet stream. A weakened gradient produces a slower, more meandering jet stream that redistributes atmospheric angular momentum differently than a strong zonal one. In this model, the surface acceleration is primarily an atmospheric response to an ice force circulation change, and the core dynamics, while real and contributing, are secondary rather than dominant. The prediction from this framework is that the acceleration will broadly track the trajectory of Arctic warming, continuing as long as ice loss continues, and potentially intensifying as feedback loops strengthen. The third is the electromagnetic coupling model. This framework, the most speculative of the three, but not without physical basis, holds that the weakening of the magnetic field, particularly in the South Atlantic region, is changing the electromagnetic coupling between the outer core and the lower mantle. A weaker coupling means less rotational resistance between the two layers, allowing the core to transfer angular momentum to the mantle more efficiently. The result is a transient increase in the rotation rate of the mantle and the crust above it. In this model, the surface acceleration is a symptom of a magnetic transition, possibly an excursion, possibly the early stages of a full reversal, rather than a cause and effect sequence flowing from the core through purely mechanical pathways. The prediction is that the acceleration will continue and may intensify as the coupling weakens further, then reverse when the field begins to strengthen again or the coupling regime undergoes a more fundamental change. Each of these models has published empirical support. Each has published critiques. None has been falsified by available observations. What all three share is a recognition that the current situation is not noise. It is not a random fluctuation in an otherwise stable system. There is a physical story being told in the data. The scientific debate is about which chapter of that story we are currently reading, and how the chapters yet to come will unfold. When you look at what the models agree on, setting aside their disagreements, one picture emerges that is clearer than any individual theoretical framework. When all the independent signals described in this account are mapped together on a single timeline and examined for their pattern of departure from historical baselines, what appears is not random. Something changed across multiple Earth systems simultaneously, with the changes becoming visible in the data across a single decade. And system-wide, correlated changes in Earth's coupled geophysical behavior do not stabilize quickly. The geological record shows that when multiple systems enter a departure phase together, they tend to remain in that departure for decades to centuries before finding a new equilibrium. And the equilibrium they find is not identical to the one they left. The planet finds a new normal. It has done this before, across billions of years of history. What has not happened before, at least not in the geological interval that matters most, is that the transition coincided with the existence of a global civilization built to operate in the old normal. The phrase, Earth's rotation, affecting daily life, sounds abstract. It sounds like a concern for physicists and satellite engineers, and not for anyone who simply wants to live their life, pay their bills, catch a flight, and have a reliable power supply. Here's why that assumption is wrong in ways that become more consequential with each passing year. Every commercial aircraft flying today navigates using a combination of satellite positioning, inertial reference systems, and radio navigation aids. All of these systems are synchronized to coordinated universal time. When a flight departs one continent and arrives at another 10 hours later, the navigation computers have been tracking position continuously against a model of Earth's orientation in space that was current at the time the flight began. Any inaccuracy in that model, any divergence between the assumed orientation and the actual one, propagates directly into position error throughout the flight. Modern aircraft use GPS-based approach procedures that are certified for use in visibility conditions, where pilots cannot see the runway until they are 100 feet above it or less. The lateral tolerances on these approaches are measured in meters. The vertical tolerances are measured in feet. These are not engineering approximations. They are the boundaries within which the system must perform to guarantee safety for the aircraft and the people aboard it. The systems delivering that precision are the same systems that depend on Earth rotating within a predictable range. Aviation safety authorities have already acknowledged the changing environment. Technical bulletins from regulatory bodies in multiple countries have noted that increasing anomalies in Earth's geomagnetic and rotational behavior require more frequent updates to navigation databases. The standard update cycle for aviation navigation data has historically been 28 days. Certain categories of data, particularly magnetic variation data used for runway alignment and approach procedure calculations, are now being reviewed and updated on shorter cycles in response to the accelerating rate of Core-mantle. Magnetic pole movement, power grids present a different, but equally concrete set of vulnerabilities. Alternating current flows at a fixed frequency 50 Hz in most of the world, 60 Hz in North America and parts of Asia. Grid operators synchronize the phase of current across interconnected systems spanning thousands of miles by referencing coordinated universal time continuously. When two sections of a grid run slightly out of phase, energy does not transfer efficiently across the connection. When the phase mismatch grows beyond design tolerances, automatic protective systems disconnect sections to prevent equipment damage. Those protective systems are calibrated to thresholds established through decades of operating experience, under conditions where the timekeeping environment was stable and predictable. Unusual timekeeping conditions, even subtle ones, even those that fall well short of the dramatic negative leap, second scenario can produce phase behaviors that fall outside the calibration range of protective systems designed for more ordinary conditions. Grid operators in Europe and North America have both published technical analyses examining how timekeeping anomalies propagate into grid behavior. Both analyses concluded that existing protective systems are adequate for the current level of anomaly. Both also noted that recalibration would be required if the anomaly grew significantly beyond its present range. The hospital system is the least obvious example on this list, and arguably the most serious in its potential consequences for individual human lives. Modern hospitals are dense with time-critical systems. Medication dispensing platforms log timestamps on every dose administered, creating a legal and clinical record that must maintain strict chronological integrity for auditing and safety verification. Operating room equipment, anesthesia delivery systems, patient monitoring platforms, implantable device programmers records data against synchronized timestamps that form part of the medical record. Radiological equipment, particularly the linear accelerators used in cancer treatment, uses precise timing to coordinate radiation beam delivery with patient breathing cycles, minimizing dose to healthy tissue. In each of these applications, a significant discontinuity in the timekeeping system does not create merely a data anomaly. It creates a gap in the medical record that triggers automatic safety alerts, and in some systems triggers automatic shutdowns pending manual verification. The deeper issue is not that these systems will fail catastrophically without warning. It is that they are being maintained by dedicated, skilled teams who are spending increasing resources managing a timekeeping environment that was supposed to remain stable. Resources spent compensating for unexpected environmental changes are resources not available for other improvements. And as the underlying planet behaves more unusually, the maintenance burden grows quietly, incrementally, in ways that do not make headlines, but that accumulate in the balance sheets of the institutions responsible for keeping these systems running. In research institutions that study Earth's geophysical behavior, there is a type of data visualization that has become increasingly common in the past several years. It takes the independently measured datasets from each of the systems described in this account, the rotation record, the inner core seismic data, the outer core magnetic field measurements, the ice mass balance, the ocean circulation proxies, the atmospheric angular momentum record, normalizes them to a common scale, and plots them together on a single shared timeline. The exercise is not standard practice in any one scientific discipline, because each of those fields has its own conventions, its own preferred visualization formats, and its own professional culture of presenting findings in disciplinary isolation. But when researchers from different fields have made the effort to produce this kind of unified timeline, what they find stops the conversation. The pattern is not ambiguous. It does not require interpretive charity or selective reading of the data to see. Something changed across multiple independent geophysical systems during the same approximate decade. And the changes, viewed together, do not look like the ordinary background variability that characterizes the planet's behavior during stable periods. They look like the beginning of a departure. The inner core rotation anomaly data, referenced against the 1990s baseline established through decades of seismic monitoring, shows a clear behavioral change beginning around 2009 to 2010. The departure from the prior trend, the slowing of the inner core's over-rotation relative to the mantle above it, strengthens and becomes unmistakable through the early part of the following decade. Outer core angular momentum estimates, derived from the rate of change in the magnetic field as measured by global magnetometer networks, and subsequently by the Swarm satellite constellation, show a concurrent shift beginning in roughly the same time window. The profile of that shift is different from the inner core signal. It reflects the different coupling timescale between inner and outer core dynamics, but the timing of the departure from baseline is consistent. Surface rotation data, measured with atomic clock precision at geodetic laboratories on multiple continents, and coordinated through the International Earth Rotation and Reference System Service, shows the acceleration becoming visible above background noise around 2016. The most extreme values in the record appear in 2020, 2021, and 2022. The lag between the inner core signal around 2009 and the surface expression around 2016 is consistent with the transfer timescales that researchers modeling core-mantle coupling have estimated from first principles. Greenland ice mass loss rate, plotted against its pre-2000 baseline using the GRACE and GRACE-FO satellite gravity data, shows a step change increase beginning around 2012 and continuing to steepen through subsequent years, with no indication of stabilization in the most recent data. South Atlantic anomaly minimum field intensity, tracked continuously since high-quality satellite measurements became available, shows a consistent decline with a measurably steeper gradient emerging in the mid-2010s. The second minimum, the splitting of the anomaly into two distinct weak zones, appears in the data as a feature that strengthens through the latter part of that decade. Arctic sea ice extent, used as a proxy for the atmospheric circulation changes affecting jet stream behavior and the polar vortex, shows its sharpest sustained multi-year decline beginning around 2012, with record, or near record, minimums appearing repeatedly in subsequent years. Atlantic meridional overturning circulation strength estimates derived from ocean heat transport proxies and supplemented by direct current measurements at instrumented sections across the Atlantic, show accelerating, weakening concentrated in the mid-2010s. The most recent estimates suggest the circulation is now at a level not observed in reconstructed records extending back over a millennium. Each of these time series was measured independently. Each was produced by different instruments, different institutions, different scientific communities, operating without coordination or awareness of how their results would appear alongside the others. Each shows its most significant departure from historical baseline behavior within the same decade-long window, centered on approximately 2010 to 2020. The probability that 7 independent geophysical systems all departed significantly from their historical baselines within the same decade by pure coincidence with no shared physical driver, no common causal thread, is not zero. Complex systems do occasionally exhibit simultaneous changes through mechanisms that are difficult to trace, but the probability is very small enough that most researchers who have examined this alignment treat it as evidence of a common excitation. Something in the coupled Earth system changed during that window in a way that propagated simultaneously across multiple layers, inner core to outer core, to surface rotation, ice to ocean circulation to atmosphere, magnetic field to rotational coupling, and back. The changes are not independent. They are coupled through the same physical mechanisms that have always linked these systems. What changed is that the coupling, in this decade, began driving multiple systems away from equilibrium at the same time. System-wide changes in Earth's coupled geophysical behavior do not stabilize quickly. The geological record demonstrates this with a consistency that is one of its most important lessons. When multiple systems enter a departure phase together, when the rotation anomaly, the magnetic anomaly, the ice redistribution, and the ocean circulation change all begin moving in the same period. They tend to remain in that departure for decades to centuries before finding a new equilibrium. The systems interact too extensively and with too many feedback loops to allow any one of them to return to its prior state, while the others remain changed. And the equilibrium they eventually find is not the one they left. The planet moves to a new normal. The new normal is not worse in any absolute sense. Earth has experienced far more extreme geophysical states across its long history, and life has persisted through all of them. But it is different, and the difference matters, specifically and concretely, for a civilization that was built in the old one. The monitoring infrastructure that produced every measurement described in this account deserves attention in its own right, because the instruments and networks responsible for this knowledge are among the most extraordinary scientific achievements of the modern era, and among the most underfunded relative to the scale of the questions they are answering. The International Earth Rotation and Reference Systems Service, headquartered in Paris, is the coordinating body for Earth rotation monitoring globally. It collects data from a worldwide network of very long baseline interferometry stations and facilities that use large radio telescopes pointed at distant quasars to measure Earth's orientation in space with precision that has no parallel in any other measurement technique. The quasars are key to understanding why this works. They are so enormously distant, billions of light years away, that their apparent positions in the sky do not change measurably, even over decades of observation. They are, for practical purposes, fixed points in the universe. Any change in how Earth is oriented in space, any change in its rotation rate, its rotation axis, or the wobble of its poles shows up as a change in the apparent angular position of the quasar signal, as measured simultaneously at multiple stations around the world. By comparing those signals with nanosecond precision, analysts can reconstruct Earth's orientation in space at a given moment to within a fraction of a milliarcsecond, a measurement of angle so small that it corresponds to the apparent width of a human hair seen from hundreds of miles away. The VLBI network has stations in North America, Europe, Asia, Australia, and Antarctica. It operates continuously, processing data from multiple telescopes simultaneously to produce the Earth orientation parameters that satellite operators, navigation system administrators, and timekeeping authorities rely on. The parameters are published every few days, and the updates have been requiring larger corrections adjustments further from the expected baseline, with greater frequency since 2016 than in any comparable preceding period. The magnetic field is monitored by a separate but equally impressive infrastructure. Ground-based magnetometer networks distributed across every continent have been recording the field's strength and direction for over a century in some locations, providing a continuous time series of remarkable length. But the most detailed and globally consistent picture of the field's current state comes from space. The European Space Agency's SWARM mission, a constellation of 3 satellites flying in carefully coordinated orbits, maps the global magnetic field from space with spatial resolution and temporal consistency that ground networks cannot match on their own. SWARM has been producing data since 2013, and the picture it has assembled of the South Atlantic anomaly's growth, the global field's slow weakening, and the shifting position of the magnetic poles is the most detailed in the history of geomagnetism. The inner core is monitored through seismology, which means it is monitored indirectly through the waves that major earthquakes send radiating through the planet's interior. The global seismographic network operates more than 150 broadband seismograph stations distributed across every continent and many remote islands, chosen for locations that combine geological stability with distance from human-generated noise that would interfere with the sensitive instruments. Every significant earthquake anywhere on Earth sends waves through the core that are recorded simultaneously at dozens of these stations. The dataset grows with every major seismic event and is maintained and curated continuously by teams at institutions across the United States and internationally. The ice sheets are monitored by the Graceful mission, 2 satellites flying in formation at an altitude of roughly 350 miles, tracking the distance between themselves to within a fraction of a micrometer using microwave ranging instruments. Changes in Earth's gravitational field caused by shifts in ice and water mass, create changes in that inter-satellite distance that can be translated, through careful processing, into maps of mass change at the surface, with spatial resolution of a few hundred kilometers. The measurement is continuous and global. No other technique can measure the total mass balance of the ice sheets with comparable accuracy and consistency. These systems are extraordinary achievements. They represent decades of scientific effort, billions of dollars of investment, and the sustained international cooperation that only the most compelling scientific questions attract. But they are also under continuous pressure. Maintaining aging hardware in remote locations is expensive. Expanding the networks to fill gaps in coverage requires sustained funding that is not always available. The Southern Ocean is one of the most dynamically important and least monitored regions for the rotation budget, storm activity, and ocean-atmosphere interaction. There redistributes angular momentum in ways that are significant, but poorly constrained because the observing station network is sparse. Proposals to expand Southern Ocean monitoring have been partially funded but not fully implemented. The gap in the observing system is a gap in understanding the rotation budget. The deep ocean circulation is monitored by an array of instrumented floats and moored sensors that collectively represent a tremendous achievement in observational oceanography, but which still leaves large regions of the deep ocean unsampled on timescales relevant to the changes currently underway. The core is monitored entirely through the indirect method of seismic wave analysis. No instrument has ever survived the journey to the core-mantle boundary, let alone to the inner core itself, and the prospects for direct measurement of the core's behavior remain remote. What the existing monitoring infrastructure does tell us is, nonetheless, substantial and unprecedented. The anomaly is real. It is growing. The causes are partially understood and partially open questions that active research is working to resolve. The rate of change across multiple systems is faster now than at any point in the modern instrumental record, and the geographic and temporal alignment of those changes points toward shared causation rather than coincidence. 3 scientific teams working independently over the past several years have each attempted to build models that incorporate core dynamics, ice redistribution, ocean circulation, and atmospheric angular momentum simultaneously to produce integrated projections rather than single system ones. Their conclusions overlap in some areas and diverge significantly in others. The disagreements are not signs of weak science. They are signs that the problem is genuinely hard, that the number of interacting variables, the imperfect observational coverage, and the absence of historical analogs for the current combination of forcing conditions all conspire to make confident projection difficult. But all 3 teams agree on one thing that stands above the specific disagreements. Whatever trajectory the system follows from this point, it will not simply return to where it was. The baseline has shifted. The new baseline is still being established. 500 million years ago, Earth was a profoundly different world. The continents were arranged in configurations that no modern map would recognize. Life existed almost entirely in the oceans. The most complex animals were arthropods and early mollusks. The atmosphere had a different composition. The star this planet orbits was slightly dimmer than it is today, and the rotation was noticeably faster days, roughly 22 hours long, a year containing more than 400 of them. The moon was closer than it is now. Tidal breaking was more intense. The deceleration curve over the following hundreds of millions of years was correspondingly steeper than it has been in the recent geological era. The ancient tidal rhythmite record from this period, preserved in sequences of layered mudflat sediments in places like the Flinders Ranges of South Australia and the Precambrian sequences of northern China, is detailed enough to reconstruct not just the approximate length of the day, but the seasonal variation in tidal patterns. From that seasonal variation, researchers can extract the moon's distance at the time of deposition and the obliquity of Earth's rotational axis, the degree to which the planet was tilted relative to its orbital plane. What those records reveal is not just a faster rotation. They reveal a planet that was, by the standards of the last few 100 million years, geologically extremely active. The period spanning roughly 500 million to 450 million years ago includes one of the most intense global glaciations in Earth's history, followed by rapid warming, followed by another period of glaciation. It includes the largest mass extinction event before the end Cretaceous event that ended the age of non-avian dinosaurs, a series of extinction pulses called the Late Ordovician mass extinction that eliminated roughly 85% of marine species. The causes of that extinction are complex and still debated, involving interactions between glaciation, sea level change, and ocean chemistry shifts that played out over millions of years. The correlation between extreme rotational and geophysical conditions and biological upheaval during this period does not establish rotation as the cause of the extinction. Earth's history is complex enough that correlations in the deep past are always difficult to interpret causally with confidence. But what the record does establish is the range of what Earth has actually done, documented in the physical archive of rock and sediment, not inferred from theory. Earth can shift its rotation by multiple milliseconds per day over decades. It can shift its spin axis by measurable fractions of a degree over centuries. It can sustain geomagnetic excursions for thousands of years, during which field intensity drops to a fraction of its normal value. It can produce volcanic episodes in deglaciated regions lasting tens of thousands of years. It can redistribute mass between the poles and the equator rapidly enough to leave detectable signatures in tidal sediments laid down at the margins of vanished seas. These are not hypothetical extremes constructed by modelers working at the edge of their assumptions. They are documented events in the geological record, confirmed by multiple independent lines of evidence. The current changes, viewed against this deep historical backdrop, are not at the extreme end of what Earth has done. They are well within the planet's demonstrated range of behavior, but they are meaningfully outside the range of the last 10,000 years. The Holocene, the epoch during which human civilization developed, agriculture was invented, cities were built, trade routes were established, and every piece of infrastructure that modern life depends on was designed and constructed. That is the relevant comparison for the present moment, not whether Earth has been through worse. It has, repeatedly, and on scales that dwarf what we are currently observing. The relevant question, the one that matters for the people living now and for the institutions responsible for the systems that support them, is whether the infrastructure built during a period of extraordinary geological stability is resilient enough to operate reliably as conditions move, outside the stable range that made its construction possible. The honest answer is, some of it is, and some of it is not. And which parts fall into which category is not always obvious from the outside, because the systems most vulnerable to geophysical anomalies are often not the ones that look most fragile at first glance. The aging power transformer and the state-of-the-art financial exchange platform are both vulnerable in different ways to the same underlying perturbation in the timekeeping environment. The century-old harbor wall and the recently completed airport both face the same changed sea level baseline. The resilience of a system to geophysical change is not simply a function of how modern or well-maintained it is. It is a function of how closely its design assumptions match the conditions it was built to operate in, and how much margin it has when those conditions change. The researchers who have looked most carefully at the aggregate picture, who have laid all the signals together and tried to read what the combined pattern says, have identified one feature that appears consistently whenever Earth's geophysical systems show this degree of simultaneous change. It is not a specific catastrophe. It is not a single event that can be circled on a timeline. It is a period of heightened sensitivity. During a geophysical transition, when multiple systems are simultaneously departing from their prior equilibria, the coupled Earth system operates in a configuration where small additional forces can produce disproportionately large responses. A modest perturbation that would produce a modest, easily absorbed effect during a stable period can produce a much larger effect during a transition because the system's own feedbacks are already amplifying changes rather than damping them. Tipping points that were safely distant during stable conditions become reachable with much smaller external pushes. The history of this planet is written in transitions. The record of those transitions, read from rock and sediment and ice, makes clear that the dangerous part of any geophysical shift is not the new state at the end of it, the new equilibrium toward which the system is moving. The dangerous part is the journey, the transit between states, the period during which multiple systems are simultaneously adjusting, when the feedbacks are running, when small perturbations find an amplifying system rather than a stabilizing one. That transit is not approaching. It is not a future risk to be planned for at some comfortable remove. The measurements described throughout this account make clear that the transit is already underway. It began, as best the data can establish, during the decade spanning approximately 2010 to 2020. It is continuing. Its endpoint, the new equilibrium that the planet's coupled systems will eventually find, is not yet determinable from available observations. What is determinable is the direction of travel. The rotation axis is moving. The magnetic field is weakening. The ice is redistributing. The oceans are changing. The core is behaving differently. These are not model predictions subject to revision when assumptions are refined. They are measurements, taken by instruments calibrated against the most precise physical standards available, reviewed by multiple independent teams, published in the peer-reviewed scientific literature, and now accumulating into a pattern that is difficult to misread. The picture described throughout this account did not emerge from a single laboratory or a single satellite or a single scientific community working in isolation. It came from a distributed, often underfunded, globally coordinated network of scientists who spend their careers measuring things that most of the world does not know are being measured. People who spend years in remote locations maintaining instruments. People who process vast quantities of data looking for signals that are small by everyday standards, but enormous by geological ones. People who communicate their findings in the careful, hedged, professionally conservative language of peer review language that does not always translate well into the directness that the findings deserve. What those findings say, taken together and stated plainly, is this: Earth is rotating faster than it has in 50 years of precise measurement. The inner core has changed its rotational behavior in a way that has no clear precedent in the observational record. The outer core circulation is different from what it was 2 decades ago, and the difference is visible in both the rotation data and the magnetic field data. The magnetic field has weakened globally and dramatically in the South Atlantic region, where a structure in the outer core is growing in a way that is connected to both phenomena. The ice sheets are losing mass at rates that were not expected under most scenarios until much later in this century, and that mass loss is physically shifting the planet's axis and changing its moment of inertia in real time. The ocean circulation is weakening. The atmosphere is responding to all of the above and feeding changes back into the rotation budget through coupling mechanisms that are well understood and continuously observed. These changes share a common origin in the sense that matters most. They are all products of the same coupled Earth system responding to forcing conditions that have moved outside the range of the last several thousand years. They are not separate stories. They are the same story, told simultaneously in different languages: the language of seismology, the language of geomagnetism, the language of glaciology, the language of physical oceanography, the language of atmospheric dynamics, but describing the same underlying transition in the same planetary system. The timekeeping infrastructure that coordinates global communications feels this transition as an unwanted drift between atomic time and Earth time. The satellite navigation systems feel it as position errors that require increasingly frequent correction. The power grids feel it as phase anomalies that push protective systems toward their calibration limits. The aviation system feels it as an accelerating pace of navigation database updates and an increasing frequency of timing-related technical bulletins. The hospitals feel it as an expanding maintenance burden on the time-critical systems that form the backbone of clinical record-keeping and treatment delivery. The people living on low-lying coastlines feel it as seas that are rising faster than the models that justified their infrastructure investment predicted. Each of these is a real, documented effect of real, documented geophysical changes. None of them, in isolation, represents a crisis that demands immediate emergency response. Together, they represent a system under increasing stress, a civilization designed for one version of this planet, operating in a version that is slowly but measurably becoming different. Human civilization was built during one of the most geodynamically stable periods of the last several 100 million years. The 10,000 years since the end of the last glaciation were, by the standards of Earth's long history, extraordinarily quiet. Rotation varied within a narrow band. The magnetic field was relatively stable, neither reversing nor undergoing a major excursion. The ice sheets retreated at a pace that allowed coastal landmasses to adjust and sea levels to stabilize over centuries. The climate, while not uniform across the Holocene, remained within a range that permitted the development of agriculture in multiple independent regions, on multiple continents, the foundation on which every subsequent human achievement was built. In that stability, we built cities at coastal elevations that assumed sea level would not change rapidly on the timescales of urban infrastructure decades to centuries. We built satellite navigation infrastructure that assumed Earth would rotate within a predictable, historically observed range. We built power grids and financial clearinghouses and hospital networks that assumed the clock would run smoothly and that timekeeping corrections would be rare, modest, and additive. We built aviation safety systems that assumed the magnetic poles would move slowly enough that navigation databases updated every 4 weeks would remain accurate between updates. We built the entirety of modern industrial civilization on the assumption that the geophysical conditions of the Holocene were the conditions we would continue to operate in indefinitely. Every one of those assumptions is now being tested. Not all at once, not dramatically, not in the form of a single event that unmistakably announces the change, but consistently in a direction that creates compounding pressure on systems built for a different planet at a rate that has accelerated significantly in the past decade. The question that the scientific community is working hardest to answer right now is not whether these changes are happening. They are. The observational record is not in serious dispute. It is not whether they are connected. They appear to be through the same physical couplings that have always linked Earth's geophysical systems. The question, the one that shapes every practical decision being made about infrastructure investment, navigation system design, timekeeping policy, and coastal planning is how fast the transition will proceed, and whether the coupled feedbacks will stabilize at a new equilibrium within the next few decades or continue amplifying. The difference between those two scenarios is enormous. If the system stabilizes within a generation, if the angular momentum transfer from the inner core completes without triggering further large-scale rotational change, if the ice loss rate plateaus, if the magnetic field's weakening slows and begins to recover, then the engineering problems created by the current anomaly are large but finite. The corrections needed are well within the range of what the institutions responsible for global infrastructure have managed before. The adaptation is difficult but achievable with sustained commitment. If the feedbacks continue to amplify, if the ice loss accelerates into a meltwater pulse regime, if the magnetic field continues weakening toward excursion or reversal, if the inner core is changed, behavior produces further rotational consequences that have not yet propagated to the surface, then the window for managed adaptation narrows. The corrections needed grow faster than the systems responsible for implementing them can operate. The margins become insufficient one at a time, in sequence, in the way that complex systems under stress tend to fail not all at once, but in a cascade that begins with the most vulnerable components and works outward. Neither scenario is certain. And the honest acknowledgement from the researchers closest to the data, the people who have spent careers measuring these systems and who understand their behavior better than anyone else on Earth, is that the uncertainty is larger today than it was a decade ago, and not smaller. More monitoring has revealed more change. Better models have revealed more interconnection. And more interconnection means more ways for a change in one system to propagate into consequences in others that were not anticipated when the models were built. The planet you live on is not static. It never has been. Across 4.5 billion years of history, it has been through events that would render the current anomalies invisible by comparison magnetic reversals that lasted thousands of years, glaciations that buried continents under miles of ice, volcanism on scales that altered the global atmosphere, extinctions that eliminated the majority of living species and reset the trajectory of life. Earth has survived all of it. The geological record is a record of survival and adaptation across timescales that make human civilization seem like a brief footnote. But there is a difference between what Earth has survived and what human civilization has been built to withstand. The former is the story of a resilient planet. The latter is the story of infrastructure designed in the Holocene. For the Holocene, by people who had no reason to expect that the Holocene's unusual stability was not the permanent condition of the planet. It is not the permanent condition. It never was. It was a window, a long one by human standards, but a brief one by geological ones. during which the conditions happened to align in a way that made cities and agriculture and global connectivity possible. That window is not closing catastrophically. There is no event horizon, no cliff edge beyond which everything changes instantly. What is happening is more gradual and in some ways more difficult to respond to because of that gradualness. A slow, persistent departure from the conditions that civilization was built within, occurring across systems that most people never think about because those systems worked reliably for so long that their existence became invisible. The rotation of the Earth is the most fundamental rhythm of human experience. It divides day from night. It sets the pace of every biological clock. It makes the GPS navigation work, the satellite phone connect, the power grid synchronize, the aircraft land safely in the dark. It is so reliable, so consistent in everyday experience, that its existence as a physical phenomenon, something with a rate that can change, driven by forces that can shift, coupled to systems that can evolve, is easy to forget entirely. What the data assembled in this account says is that this most fundamental of rhythms is changing. It is changing faster than at any point in the modern era of measurement. It is changing in ways that are connected to other fundamental changes in the same planetary system. And the full consequences of those changes, the surface expression of forces currently propagating through iron and ice and ocean and atmosphere toward the systems that human life depends on, are still in transit. The instruments are running. The data is coming in. Researchers in geodetic laboratories, in seismology institutes, in remote Antarctic field camps, and in satellite operations centers are watching signals that most of the world does not know are being watched. They are measuring the answer to a question that the planet itself is asking, a question written in the language of milliseconds and magnetic field lines, and shifting ice and liquid iron moving in the dark 2,000 miles beneath your feet. The question is simple. It is the one question that sits at the center of every model, every dataset, every late-night conversation in geophysics departments, and over conference tables in rooms where people who understand what the data actually says gather to share what they know and acknowledge what they do not. How fast? How fast is the transition proceeding? How fast will the equilibrium shift? How fast will the consequences arrive at the surface, at the navigation systems and power grids and coastlines and timekeeping infrastructure that were built for a different version of this planet? That answer is being written right now. It is being written in the motion of ice you cannot see from where you are standing. It is being written in the circulation of an ocean of liquid iron, more than 2,000 miles below your feet, moving in total darkness under pressures that no instrument has ever directly measured, generating forces that take years and decades to reach the surface, but that arrive, eventually, with the patience of a planet that has been in motion for 4.5 billion years, and intends to remain so for billions more. The planet is not in danger. It has been through worse, and will continue long after whatever transition is currently underway has resolved into a new equilibrium that future scientists will study the way current scientists study the last glacial maximum as a defined period with a beginning and an end, comprehensible in retrospect, written clearly in the geological record for those who know how to read it. What is in question is not the planet. It is the version of human civilization that was built during the brief, unusual, extraordinarily fortunate stability of the Holocene, and whether the institutions and systems and infrastructure that stability made possible are equal to the task of operating in conditions that are day by day, year by year, measurement by measurement, becoming something different. That is the question the planet is posing. The answer depends on how carefully we listen to what the instruments are saying, and on whether the people in a position to act on what the data shows choose to do so before the window for managed adaptation closes, and the work of responding becomes something considerably harder than it needs to be. The data is coming in. The signals are in the rock, and the ice, and the magnetic field, and the precise fractional timing of each day's rotation. The planet is speaking in the only language it has ever used, the language of physics, operating on timescales longer than history, through mechanisms more powerful than anything we have built. The question is not whether we are capable of understanding what it is saying. The question is whether we choose to.